About 4.54 billion years ago, Earth was not yet a habitable planet. It was not even a stable planet in the way we understand it today. It was a forming body, born from the protoplanetary disk of the young solar system, where matter was still aggregating under the pull of gravity. At that time, Earth's surface was largely covered by a global ocean of magma. Scientific estimates place the surface temperature between 1,500 and 2,000 degrees Celsius, high enough to keep rocks in a permanently liquid state. There was no lasting solid crust. Every attempt at solidification was immediately destroyed by impacts, volcanic eruptions, or the planet's still extreme internal heat. Earth was literally a molten world. But that was not the only source of chaos. The young solar system was still filled with debris left over from the formation of the planets. It was a phase of constant collisions. Between about 4.1 and 3.8 billion years ago, Earth underwent what scientists call the Late Heavy Bombardment. During this period, millions of asteroids and protoplanets still struck the inner planets. Some impacts released energy equivalent to billions of megatons of TNT, enough to instantly vaporize entire oceans or remelt massive portions of Earth's surface. So Earth was not only hot, it was constantly being destroyed and rebuilt. In this context, the very notion of geological stability did not yet exist. The planet oscillated between partial solidification and total destruction. Heavy materials began to sink toward the center, gradually forming a metallic core composed mainly of iron and nickel, while lighter elements rose toward the surface. This process of internal differentiation was essential. It would later allow the creation of a magnetic field, but at this stage, it was still incomplete and unstable. The primitive atmosphere was just as extreme. It contained virtually no free oxygen. It was dominated by carbon dioxide, water vapor, and nitrogen, along with volcanic gases such as sulfur dioxide and methane. Atmospheric pressure was probably much higher than today, and the greenhouse effect was massive. As a result, heat was trapped at the surface, preventing rapid cooling. Volcanoes played a central role in this environment. At that time, volcanism was far more intense than what we know today. Some estimates suggest that Earth's early internal heat flow was as much as 3 to 4 times higher than the current one. Global eruptions continuously released billions of tons of gas and particles into the atmosphere. The sky was therefore saturated with dust, ash, and aerosols. Sunlight was heavily filtered, creating a dark, unstable, and unpredictable environment. And yet, despite this total chaos, Earth slowly began to evolve into something more structured. Gravity continued to compact the planet. The elements separated. The core gradually stabilized. But this process was constantly disrupted by external events. One of the most important was the giant impact of Theia, a body about the size of Mars, around 0.1 Earth masses, collided with the proto-Earth at an estimated speed between 10 and 20 kilometers per second. The energy released was sufficient to liquefy a large part of the planet and eject an enormous amount of material into orbit. This material formed a circumterrestrial disk composed of vaporized silicates and rocky debris. It is from this disk that the Moon was born. The accretion process likely lasted from a few thousand to a few million years, which is extremely fast on a geological timescale. But this event did not immediately stabilize Earth. On the contrary, it plunged the system into a new phase of imbalance. Debris continued to fall back onto the planet. The orbital environment was unstable. Earth and the Moon were still very close, and their gravitational interactions were far more intense than today. And above all, Earth remained totally uninhabitable. Even after this impact, the surface remained largely molten. The first signs of oceans appeared later, but they looked nothing like today's. They were hot, acidic oceans, laden with carbon dioxide and sulfur compounds, with temperatures that could approach or exceed 100 degrees Celsius in some regions. At this stage, Earth was not a living world. It was an unstable thermal system, permanently transitioning between destruction and cooling. But something was slowly beginning to change. After the most violent phase of its formation, the Earth enters a slow transition. But one thing must be understood. This is not a return to calm. It is simply a change in the type of chaos. The internal heat flow remains extremely high. It is estimated that the early Earth released up to 3 to 4 times more thermal energy than it does today. This means the planet continues to behave like an unstable system, with surfaces that are rebuilt, destroyed, and reconfigured constantly. Gradually, a fundamental phenomenon begins to transform the Earth's internal structure: planetary differentiation. Under the effect of gravity, the heaviest materials, mainly iron and nickel, migrate toward the center of the planet. This is how the Earth's core forms. This core is not a detail. It is massive. It represents about 30% of the Earth's total mass. And above all, it is still partially molten at this time. Around it, convection movements begin to organize within the Earth's mantle. These movements will, in the long term, be responsible for plate tectonics. But at this stage, nothing is stable yet. Everything is still forming. It is also during this phase that the Earth begins to develop an element crucial to its future: the magnetic field. This field is generated by what scientists call the geodynamo. The principle is simple but powerful. The movement of liquid iron in the outer core produces electrical currents, which in turn generate a magnetic field. This field begins to emerge when the planet reaches a sufficiently organized internal structure. Its importance is hard to overstate. Without a magnetic field, Earth would be directly exposed to the solar wind, a constant flow of charged particles from the Sun at speeds that can reach 400 to 800 kilometers per second. On Mars, the absence of a global magnetic field is one of the major reasons for the gradual loss of its atmosphere. On the early Earth, this field therefore acts as a growing shield, even if it is still unstable and imperfect. Meanwhile, the surface slowly begins to evolve. Progressive cooling allows the formation of an initial Earth's crust. But this crust is extremely fragile. It forms, cracks, then is recycled into the mantle by internal movements. This is not yet plate tectonics as we know it today, but a primitive version, far more chaotic and unstable. The first oceans also begin to appear. Contrary to what one might imagine, they do not result only from rain. They come from a mixture of water vapor released by volcanoes and the input of ice-rich asteroids. When the surface temperature drops enough, this vapor condenses and falls back as torrential rains that potentially last thousands of years. This is how the first oceans form. But these oceans are very different from today's. Geochemical analyses and climate models suggest they were hot, often close to 70 to 100 degrees Celsius in certain regions. They were also rich in dissolved carbon dioxide, which made them acidic. These are not peaceful seas. They are chemically aggressive environments in constant interaction with an unstable atmosphere. And yet, despite this instability, a fundamental element begins to emerge: a form of local chemical stability. In certain environments, especially the deep ocean zones, temperature becomes more constant. The pressure there is high but stable. And above all, these zones are protected from extreme surface variations. It is in this type of environment that the Earth begins to become a slightly more organized system. But one major problem remains. Even if the planet gradually stabilizes, it is still very far from conditions compatible with complex life. At this stage, the Earth is not yet a living planet. It is a planet in transition, caught between a past of total destruction and a future still uncertain. And it is exactly in this intermediate zone that the most important question in this entire story begins to appear. How could something survive here? At this stage in its history, the Earth remains an extremely hostile world. Yet it is precisely within this hostility that a fundamental transition takes shape. Because even if the surface is still unstable, certain areas of the planet begin to offer surprisingly different conditions. In the primitive oceans, depth plays a decisive role. The deeper you go, the more stable the temperature becomes. Far from extreme surface variations, far from meteorite impacts and ultraviolet radiation, certain abyssal zones offer a relatively constant environment. The pressure there is immense. At 4,000 meters deep, reaches about 400 times the current atmospheric pressure. But this pressure, paradoxically, becomes a factor of stability. It is in these environments that hydrothermal vents are found, one of the most important elements for understanding the origin of life on Earth. These structures appear where seawater seeps into the oceanic crust, warms upon contact with the mantle, then rises again laden with dissolved minerals. As they emerge, these fluids can reach temperatures above 350 degrees Celsius, yet remain liquid because of the extreme pressure. Around these vents, an essential phenomenon appears: intense chemical gradients. Differences in temperature, pH, and chemical composition create environments where energy circulates continuously. And in the chemistry of life, energy is the fundamental condition of all organization. Contrary to the intuitive idea that life would need perfect conditions, modern science shows something very different. Life does not arise in equilibrium. It arises in disequilibrium, in gradients, in flows, in zones where energy can be exploited. This is precisely what hydrothermal vents provide. Spontaneous chemical reactions occur there, involving in particular hydrogen, carbon dioxide, sulfur, and various metals present in the Earth's crust. These reactions can produce simple organic molecules, considered the fundamental building blocks of life. Current scientific models suggest that the first forms of metabolism could have appeared in these environments, long before the existence of complex organisms. Chemical systems capable of sustaining themselves, partially reproducing, and transforming their environment on a small scale. We are talking here about extremophilic organisms, or precursors of life, capable of surviving in conditions that we today consider completely hostile. High temperatures, total absence of light, extreme pressures, unstable chemistry. And yet, not only is life possible there, it might even have been born there. The first microorganisms, as we understand them today, were not visible forms of life. They were invisible to the naked eye. Extremely simple unicellular structures, probably close to modern bacteria. But their importance is immense, for they represent the first moment when matter ceases to be solely physical and begins to become biological. This shift is fundamental. In a universe dominated by thermal and chemical chaos, a local organization manages to maintain itself, to exploit available energy, and to persist. And that is where the most important rupture in all of Earth's history occurs. In a world that, in theory, should allow no lasting stability, life finds a way to exist. But this is not a stable environment. These forms of life do not live in a peaceful world. They live in extremely limited niches, surrounded by an environment that is globally destructive. They survive in extreme conditions because they exploit precisely those extremes. And this reality completely changes the perspective. For if life can appear here, in such a hostile environment, then the boundary between the impossible and the possible becomes far blurrier than we had imagined. And yet, even at this stage, Earth is still far from becoming a habitable planet in the modern sense of the term. What life has just opened is only an extremely narrow door in a world still largely dominated by instability. For hundreds of millions of years, Earth remains a world dominated by extreme environments. But gradually, an invisible change on the human scale begins to transform the planet in depth. This change does not come from a single event. It comes from life itself. The first forms of life, which appeared in the primordial oceans, are extremely simple. They are unicellular microorganisms capable of surviving without oxygen, in environments rich in reduced chemical compounds. For a long time, these forms of life dominate the planet without profoundly altering its overall balance. But that is going to change. About 2.7 to 2.4 billion years ago, a major event occurs: the Great Oxidation. It is one of the most important turning points in Earth's history. For the first time, oxygen begins to accumulate in large quantities in the atmosphere. This oxygen did not appear spontaneously in the air. It is produced by a fundamental biological process: photosynthesis. Organisms called cyanobacteria use the sun's energy to transform carbon dioxide and water into organic matter, releasing oxygen as a byproduct. At first, this oxygen does not remain in the atmosphere. It is immediately absorbed by the oceans and rocks, notably by dissolved iron in the water, which oxidizes and forms characteristic deposits called banded iron formations. For hundreds of millions of years, oxygen is thus trapped in rocks before it can accumulate in the air. But once these reservoirs are saturated, oxygen begins to accumulate freely in the atmosphere. And that is when the planet changes radically. For the majority of life forms existing at that time, oxygen is toxic. What had been a stable world for anaerobic organisms gradually becomes a hostile environment for them. This transition is believed to have caused one of the first major mass extinctions in Earth's history. But at the same time, this transformation opens up an entirely new possibility. Oxygen enables chemical reactions that are far more energy efficient. In other words, it makes possible a much higher level of biological complexity. It is from that moment that Earth slowly begins to become a planet capable of hosting more complex forms of life. But this transformation is not limited to the atmosphere. It also affects the oceans, geology, and the planet's chemical cycles as a whole. Over time, oxygen also transforms the chemistry of the oceans and the Earth's crust. It alters the composition of minerals, influences the carbon cycles, and contributes to the gradual stabilization of certain environments. In parallel, Earth continues its internal cooling. The residual heat from its formation slowly decreases, allowing the gradual consolidation of the Earth's crust. This crust becomes thicker, more stable, and eventually fragments into moving plates. This is the beginning of plate tectonics as we know it today. This mechanism is essential. Tectonics makes it possible to recycle carbon, stabilize the climate over long periods, and maintain sufficient geological activity to support complex chemical cycles. Without it, Earth would be far more unstable climatically. Gradually, the oceans stabilize. They are no longer dominated by constant extreme conditions. Their chemistry becomes more balanced, their temperature more moderate, and their composition more compatible with growing biological diversity. the atmosphere too continues to evolve. The presence of oxygen allows the formation of an ozone layer in the upper atmosphere, capable of filtering a large part of the sun's ultraviolet radiation. This natural shield considerably reduces the damage caused by solar radiation at the planet's surface. It is a major transformation. For the first time, the Earth's surface becomes partially protected from the most extreme conditions of space. At this stage, Earth is no longer an entirely chaotic world. It gradually becomes a structured planet with interconnected climatic, geological, and biological systems. But this stability remains fragile. It rests on an extremely precise balance between the atmosphere, the oceans, geology, and life itself. A significant variation in one of these systems could still completely disrupt this balance. And that is where a shift in perspective occurs. Because what we today call a habitable planet is not a simple state. It is a dynamic balance maintained for billions of years by a constant interaction between opposing forces. Earth, therefore, did not become stable by chance. It became stable through a succession of slow, violent, and deeply interdependent transformations. And yet, even with this newly acquired stability, one question remains in the background. How could a system so fragile, so complex, and so dependent on multiple parameters have remained coherent long enough to allow the emergence of complex life? And then, us. After billions of years of extreme transformations, Earth finally enters a phase that we recognize as habitable. But this word can be misleading. Earth did not become stable in an absolute sense. It became stable in a dynamic balance, constantly maintained by opposing forces. Today, Earth is a rocky planet, located about 150 million kilometers from the Sun, an average distance that places it in what is called the habitable zone. This zone is not a guarantee of life. It is simply a region where conditions theoretically allow liquid water to exist on the surface. But even within this zone, everything depends on a set of extremely precise parameters. Earth's average temperature today is about 15 degrees Celsius. This figure hides a far more complex reality. Without the natural greenhouse effect, that temperature would drop to about minus 18 degrees Celsius, leaving the planet globally frozen. The greenhouse effect, mainly due to water vapor, carbon dioxide, and methane, therefore plays a fundamental role in climate stability. But this effect must remain within a very narrow range. Too weak, and Earth freezes. Too strong, and it becomes a hellish planet like Venus, where temperatures exceed 460 degrees Celsius. The current atmosphere is made up of about 78% nitrogen and 21% oxygen, with traces of other gases. This composition is not universal. It is the result of billions of years of interactions among geology, chemistry, and biology, and it remains fragile. A relatively small variation in carbon dioxide, even on the order of a few hundred parts per million, can profoundly alter the global climate. The Earth is also protected by a global magnetic field. This field, generated by movements in the liquid outer core, extends tens of thousands of kilometers into space and deflects much of the charged particles from the solar wind. Without this protection, Earth's atmosphere would gradually be eroded, as seems to have been the case on Mars. But this magnetic field is not constant. It reverses periodically. The magnetic poles switch direction, a phenomenon documented in the geological record through volcanic rocks. These reversals do not erase the field, but they show that even this fundamental protection remains dynamic and unstable on a geological timescale. The Earth is also stabilized by its moon. With a diameter of about 3,474 kilometers and a mass representing about 1/81st of Earth's, the Moon plays an essential role in stabilizing Earth's axis of rotation. Without it, simulations show that Earth's tilt could vary much more extremely, causing violent and unpredictable climate changes on relatively short timescales in geological terms. Even Earth's orbit is not perfectly stable. It depends on gravitational interactions with the other planets in the solar system, notably Jupiter, whose enormous mass indirectly influences Earth's orbital dynamics. Without this gravitational balance, Earth could undergo extreme climatic variations, or even be ejected from the solar system in chaotic scenarios. And yet, despite this complexity, Earth has maintained sufficient stability for billions of years to allow life to evolve. But this stability rests on an accumulation of extremely precise conditions. If we add up all these factors, distance from the Sun, atmospheric composition, geological activity, the presence of the Moon, the magnetic field, orbital stability, we are no longer talking about a simple, isolated chance event. We are talking about an entire chain of interdependent conditions. And that is where the paradox becomes obvious. Taken separately, each of these elements can exist elsewhere in the universe, but their simultaneous combination in a single planet, maintained over billions of years, becomes statistically much more difficult to explain. This is where two interpretations clash. The first sees Earth as an exceptional anomaly. In a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, the probability of reproducing exactly this combination of factors seems extremely low. Earth would then be a rare cosmic accident, perhaps unique on the observable scale. The second interpretation is different. It rests on the anthropic principle. We do not observe just any universe. We observe a universe compatible with our existence, because if it were not, we would not be here to observe it. In this framework, Earth is not necessarily rare or common. It is simply a necessary condition for our presence. A third possibility remains open. What if what we perceive as improbable today is only the result of physical laws still incompletely understood? In that case, the formation of habitable planets would not be an accident, but a natural consequence of deeper rules still unknown. None of these hypotheses is definitively proven, and that is precisely where modern science stands, between what we know, what we can measure, and what we do not yet understand. The Earth is therefore neither perfectly ordered nor totally chaotic. It is the result of a fragile balance maintained between destruction and stability, between chance and necessity. And at the end of this story, one conclusion is unavoidable. The Earth was not designed to
be habitable. It became habitable through a succession of violent, improbable, and interdependent transformations. And if we trace this whole history back to the beginning, one thing becomes clear. Without chaos, there would never have been us.
At the beginning of the Cenozoic era, we enter the fascinating period of the Paleogene, which spans from about 66 to 23 million years ago. This period, the first major subdivision of the Cenozoic, follows the massive extinction at the end of the Cretaceous. The Paleogene is divided into three periods: the Paleocene, the Eocene, and the Oligocene, each with its own characteristics concerning continental drift and the evolution of life. Imagine a journey across these millions of years. The lands shift, oceans are redrawn, and the first modern forms of life appear. Get ready to discover geological transformations, climate changes, and the emergence of new faunas and floras, whose traces are still visible today in rocks and fossils. At the end of the Cretaceous, a major event, often linked to the fall of a meteorite in the Yucatan, causes the abrupt collapse of terrestrial and marine fauna, particularly non-avian dinosaurs. This episode marks the symbolic boundary between the Mesozoic and the Cenozoic. At the dawn of the Paleogene, the world is upheaved and must reinvent itself. Continents continue their drift, separating or coming together according to plate tectonic movements. For example, the African and Indian plates begin movements that will lead to the Indo-Asian collision and the formation of the Himalayas. Similarly, the plates around the future Atlantic and Indo-Pacific zones rearrange, influencing the circulation of emerging ocean currents. Tectonic plates generally move a few centimeters or inches per year, but during the Paleogene, India moved at over 10 centimeters or 4 inches, an exceptionally fast pace. These rapid movements influence climate and biodiversity. The collision of plates raises mountains, altering winds and precipitation, while their separation creates new ocean basins, changing ocean currents crucial for redistributing heat on Earth. The Paleogene being vast, it has been subdivided for better understanding. The Paleocene is divided into 3 stages: Dannian, Selandian, and Thanetian. These stratigraphic markers help situate a fossil in time according to sediment layers. The Eocene, from 56 to 34 million years ago, is divided into 4 subdivisions: Ypresian, Lutetian, Bartonian, and Priabonian. Finally, the Oligocene, from 34 to 23 million years ago, includes 2 stages, Rupelian and Chattian. Each stage reflects major geological changes and ecological modifications. This division, validated internationally, serves as a reference for Paleogene researchers. Today, to refine our knowledge and establish datings, several modern scientific techniques are used. Astrochronology, which studies astronomical cycles recorded by sediments, can detect climate alternations linked to changes in Earth's orbit or axial tilt. For example, a 405,000-year cycle has been identified in the deposits of Cap Copenhagen in the Nordic regions, allowing precise calibration of geological layers. Raman spectroscopy, on the other hand, analyzes phytoliths, which are silica bodies produced by plants, helping to understand plant evolution. Megadrillings and synchrotron microtomographic analyses reveal internal fossil details, such as petrified blood vessel networks in ancient birds. Finally, mass spectrometry imagery allows the analysis of the isotopic composition of mammal dental enamel, providing information on their diet and past environment. It is interesting to recall the origin of the term Paleogene, which has not always been used in the same way by researchers. In the 19th century, the German geologist and paleontologist Heinrich Ernst von Baerek was working on tertiary limestones in the Ile-de-France. He found ancient fossils there, but not as old as those from deeper epochs. In 1829, he proposed naming these geological layers Paleogene, meaning ancient Genesis. Until then, the term tertiary was commonly used to refer to the period between the Cretaceous and the Quaternary. In 1991, the International Union of Geological Sciences divided this vast period into 2 parts, the Paleogene and the Neogene. This more precise terminology is now widely adopted. To enrich our view of the Paleogene, it is essential to consider recent discoveries that continually push back the limits of our knowledge. Between 2024 and 2025, new research uncovered several remarkable fossils, refining our understanding of the fauna of the time. In New Zealand, a giant penguin named Kumimanu fordyceae, living around 57 million years ago, was identified. After the extinction of dinosaurs, Some lines of marine birds thrived in the temperate southern seas. The Kumimanu fordyceae, measuring 1.5 meters, approximately 5 feet, and weighing over 100 kilograms, around 220 lbs, is an example of gigantism. Another recent discovery mentions a Paleogene penguin, weighing almost 355 kilograms, around 783 lbs, an impressive mass for a bird. Researchers from the University of Cambridge, having analyzed these fossils, estimate that this gigantism could result from ecological niches left vacant after the disappearance of large marine predators, favoring the evolution of increasingly large diving birds. In 2025, paleoprimatologists from Texas discovered a partial skull similar to Runea, an ancient primate already known from a few fragments. Probably dating from the early Eocene, these remains could shed light on the evolution of cranial features of primates. The analysis reveals adaptations for better 3D perception, a sharper sense of sight, or a reorganization of the brain region related to sensory processing. These results, mentioned by Kirk and his colleagues, show the importance of the Paleogene in the rise of placental mammals and primates. The Charleston Museum in South Carolina has revealed an exceptional deposit of 25 cetacean fossils dating from the end of the Paleogene to the Oligocene. This site shows a great diversity of primitive whales at a time when the planet was undergoing climate changes and the configuration of the oceans was evolving. Paleontologists see in it proof that marine mammals began to diversify early, with lines of baleen and toothed whales experimenting with various feeding and swimming strategies. This adaptive radiation marks the rise of a group that would influence the millions of years to come. In 2025, a major discovery was made with a complete skull of Diatryma, a giant bird of the Paleogene, dated to 45 million years ago and preserved in lacustrine deposits. This genus, already known for its fossils, is often nicknamed terror bird. This find has allowed a better understanding of its diet, mode of locomotion, and the structure of its nostrils, eyes, and jaws. Paleontologists are still debating whether Diatryma was an active predator or an opportunistic eater. The clues from the skull suggest a more varied ecology than previously thought. In 2025, an important discovery was made in the Caribbean with a terrestrial Sebecid crocodilian from the Upper Paleogene. The Sebecids, archaic crocodilians with a slender body and long legs, were partially or almost entirely adapted to terrestrial life. This adaptation allowed them to occupy ecological niches with less competition from large predators. This discovery, highlighted by the University of Florida, shows the diversity and specializations of Paleogene faunas, a period of large-scale evolutionary experiments. The Paleogene marks a key turning point for understanding the origin of a world more similar to ours than that of the dinosaurs. During this period, life reorganizes and evolves. Marine animals, such as archaic whales and giant penguins, explore new ways of life. Terrestrial birds, like Diatryma, dominate a changing environment. Mammals, including primates, diversify species, marking the beginnings of our evolution. These changes occur in landscapes constantly reshaped by tectonic plates and marine passages. Behind every major transition of the Paleogene lies a set of interacting geological, climatic, and biological mechanisms. Developing oceanic circulations distribute heat and nutrients, influencing marine population expansions or crises. Closed or open basins promote species diversification or isolation. Climate fluctuations, related to carbon dioxide, modify vegetation and ice caps, even though no permanent ice existed at the beginning of the Paleogene. These studies are fueled by geochemistry, stratigraphy, and paleontology, analyzing fossils and isotopes. Paleogene is a testament to the resilience and dynamism of ecosystems. This period is fascinating because it shows how life rebounded after one of the greatest mass extinctions, allowing unexpected creatures to reign in environments that no longer exist today. Fossils, found all over the world, tell stories of adaptation, expansion, and the emergence of lineages leading to contemporary biodiversity. Scientific discoveries, often shared by museums, confirm the crucial importance of this chapter, less known than the age of the dinosaurs, but just as significant for the planet's history. The Paleogene is a key bridge between the Mesozoic and the era of modern mammals and birds. Thanks to advanced methods such as astrochronology and microtomography, we better understand the transitions of this time, why certain species emerged, and what conditions allowed the appearance of giant forms or predators adapted to terrestrial or aquatic life. This chapter is an excellent starting point for exploring in depth the evolutions of the Paleogene. At the start of the Paleocene, from 66 to 56 million years ago, the planet was in full reorganization. The continental plates, guided by Earth's internal energy, continued their drift after the extinction of the major non-avian reptiles. Imagine a world in transformation, with continents moving slowly, redrawing oceans, and creating new meeting zones between land masses. This period marks the beginning of the Cenozoic, the geological age where mammals and modern flora and fauna develop. During the Paleocene, continents began decisive movements for the future configuration of the planet. North America separated from Europe, the North Atlantic formed, and India began its journey northward, setting the stage for the Himalayan collision. This journey focuses on this specific period, essential for understanding the foundations of Cenozoic tectonics. At the beginning of the Paleocene, North America and Europe were close. At the end of the Cretaceous, before the dinosaur extinction, these continents were connected by continental plates. During the Paleocene, the separation deepened. Convective movements of Earth's mantle pushed the continental blocks apart. Divergence in geology refers to the distancing of plates along an oceanic ridge where new crust forms. In the Proto-North Atlantic region, ocean floor spreading marked the expansion of the Atlantic Ocean. Iceland and the Mid-Atlantic Ridge are key points. Considered a volcanic hotspot, Iceland is situated on this ridge, often dubbed a natural laboratory of plate tectonics. During the Paleocene, the northern part of the ridge emerged due to intense volcanic activity, creating underwater reliefs and islands. Geologists and paleontologists studying marine sediments note massive eruptions, indicative of a geologically turbulent period. The basalt layers in Iceland are proof of this. Alongside the opening of the North Atlantic, India, originally in the southern hemisphere, continued its journey north. The Indian plate moved at an average speed of 15 centimeters or 6 inches per year, more than twice the speed of many other plates. This rapid movement is explained by the particular configuration of the mantle beneath the plate and the disappearance of the Paleo-Tethys Ocean between India and Asia. At that time, India traversed vast oceans before meeting the Asian continent. This swift drift would later result in the collision with Eurasia. In the Paleocene, the subtropical carbonate platforms gradually consolidated. These shallow marine zones, often in warm regions, are dominated by the precipitation of carbonates formed by carbon, oxygen, and calcium. These platforms are formed thanks to living organisms, such as corals and calcareous algae, which produce skeletons rich in calcium carbonate. They thrive in subtropical environments, characterized by warm and humid conditions, where biodiversity flourishes. These platforms support the life of many invertebrates and pioneering species that survived the end of the Cretaceous. In the Paleocene, the Tethys Sea, separating Laurasia in the north from Gondwana in the south, remains largely open. This vast epicontinental sea houses a wide variety of marine species, from small planktonic organisms to larger fish. The shallow waters of the Tethyan margin favor the formation of reefs and carbonate deposits. The Tethys Sea influences ocean circulation, creating a corridor of warm waters between the west and the east, and promotes a global climatic homogeneity. Ocean currents, by transporting heat, nutrients, and species, influence the distribution of marine fauna and flora. At the end of the Mesozoic, after the era of non-avian dinosaurs, the oceans adapt to the new configuration of the continents and the evolution of ecosystems. In the Paleocene, ocean currents begin to reorganize around the shifting continents, preparing future oceanic signatures. The emergence of new ridges, the opening of marine passages, and the modification of coastlines create new current trajectories. These changes influence the dispersion of marine species, as organisms travel through water masses circulating from one basin to another. In the long term, the formation of marine corridors and the closure of passages alter the distribution of biodiversity and the migrations of marine vertebrates. In the Paleocene, continental drift intensifies the formation of smaller-scale mountain ranges due to the compression and twisting of plates. When one plate moves away from another, the contact zones generate geological stresses that cause uplift, deformation, or folding of blocks. Although the reliefs of the time are not as imposing as those of the Himalayas or the Andes, the early tectonic movements prepare the fragmentation of Pangaea into distinct masses. Pangaea was a supercontinent that combined almost all the land masses, and its fragmentation gave birth to the Atlantic, the Indian Ocean, and other smaller basins. Geological processes influence the establishment of terrestrial faunas and floras. The initial paleogeography and tectonics designate the conditions that determine where life can establish, how it moves, and to which sectors it migrates. In the Paleocene, the planet experiences a warmer and more humid climate than today, which accentuates the role of continental platforms and terrestrial corridors formed or erased by plate movements. For example, an isthmus allows certain species to cross geographic boundaries, while an inland sea can isolate populations, generating distinct evolutions. Tectonics is the backdrop of each episode of biological diversification. The increased opening of certain basins, like the Proto-North Atlantic, is crucial for the formation of the modern Atlantic marine regions. The water circulating between these basins shapes varied shores, vast lagoons, sloped coasts with burgeoning mangroves, and deltas where large sediments are deposited. Today, geologists study these fossilized sediments to understand the distribution of past continents and reconstruct the original environment. They use modern techniques such as seismic imaging, the analysis of microfossils in marine cores, and the study of the chemical composition of geological strata, offering an accurate view of plate drift and the history of oceanic basins. India's speed to the north remains remarkable at a rate of 15 centimeters, 6 inches, per year, which is rapid on a geological scale. This rapid progress is paving the way for the India-Asia collision, which will occur during the Eocene. At the beginning of the Paleocene, the Indian plate is still traveling over a vast ocean, reducing the distance with Eurasia each year. The subduction of the oceanic plate, buried beneath Eurasia, generates earthquakes, volcanoes, and increasingly intense orogeny. However, the major collision will not occur until the turn of the Eocene, beyond the period of this text. the Tethys Sea does not merely represent a bygone past, but plays a major geographical and ecological role throughout the Paleocene. It serves as a ground for biological exchanges, allowing marine and coastal groups to move along the coasts of emerging lands. The Mediterranean, Middle Eastern, and Indo-Pacific regions were then much more connected, explaining the presence of similar faunas in the fossil records of this area. Sediments containing shells, fragments of sea urchins, or fish teeth bear witness to biological corridors crossing the Tethys Sea. The geological diversity of the Tethys Basin is reflected in the carbonate, clay, and volcanic layers, each offering a glimpse of these ancient marine environments. The Cretaceous-Tertiary crisis disrupted life on Earth, and the Paleocene becomes a time of rebuilding. The distribution of continental masses influences oceanic dynamics. Winds, temperatures, evaporation, and salinities of waters determine surface and deep currents, establishing new circulation pathways. These routes are crucial for the mixing of nutrients and the movement of heat, forming what is today called the Earth's climatic engine. Although this engine evolves rapidly, the opening or closing of straits plays a key role in the intensification or reduction of certain climatic regimes. Scientists analyze Paleocene sediments to find clues about this circulation, such as the distribution of specific minerals, planktonic fossils adapted to warm or cold climates, and the isotopic composition of shells. At the beginning of the Paleocene, the Earth resembles a hot hearth, with an atmosphere rich in carbon dioxide, with a concentration of about 1,000 parts per million, compared to about 400 today. This greenhouse gas, essential to global warmth, was far more concentrated, accentuating the greenhouse effect of the time. This high concentration was partly due to intense volcanic activity at the end of the Cretaceous, rapid decomposition of vegetation, and the release of carbon from ancient rocks. The absence of permanent glaciers amplified the heat, as the ice caps could not reflect solar light back into space. This contributed to a particularly mild, even tropical climate between 66 and 56 million years ago. In the subtropical oceans of the Paleocene, the surface temperature was around 24 degrees or 75 degrees, much warmer than the current 20 degrees to 24 degrees or 68 degrees to 70 degrees. This difference, although modest, transforms the distribution of marine life and the geographic range of species. A warmer ocean favors the multiplication of phytoplankton, the base of the food pyramid, leading to dynamic food chains. Corals and many mollusks, including cephalopods like belemnites, thrive. The latter, related to cuttlefish and squids, leave calcareous points that fossilize well and serve as indicators of past waters. To reconstruct the climatic conditions of the Paleocene, paleontologists and geologists use several methods, including the analysis of delta 18O. This term refers to the ratio of the oxygen isotope of mass 18 relative to the more common isotope of mass 16. When marine organisms such as belemnites build their shells, they incorporate a mix of oxygen corresponding to the chemical composition of seawater. The warmer the water, the less concentrated the heavy isotope, oxygen 18, is. By measuring the amount of oxygen 18 in fossils, scientists can determine the temperature at the time when the organism lived. In the Danish basin, Dannian belemnites show a high temperature, confirming subtropical conditions. The absence of permanent ice has a major impact on sea levels. Without massive ice sheets near the poles, the water that would have been frozen remains in the oceans, increasing the global sea level. Huge coastal plains disappear beneath the waves, fostering the development of shallow seas over vast continental areas. In these conditions, the Earth's surface during the Paleocene is quite different from today, with modified coastlines, disrupted distribution of ecosystems, and tropical or subtropical vegetation extending further towards higher latitudes. The poles, especially the South Pole, are a major subject of curiosity for paleontologists. During the Paleocene era, the Earth was much warmer than it is today. The term paleopole refers to the ancient location of the geographic or magnetic pole at a given time in history. With plate tectonics, the position of the South Pole changes, but at this time, it is far from the current Antarctic continent, in a region cold due to reduced sunlight. However, owing to the greenhouse effect, it remains relatively mild, even allowing the existence of tree fern forests, which indicate a subtropical or temperate climate at these high latitudes. Using fossilized pollen and spores, researchers determined the vegetation of the southern paleopole. These tiny grains, produced by plants for reproduction, are well preserved in sediments. Using tools like the nanosims, a high-resolution mass spectrometer, they can analyze these microscopic remains. This instrument bombards the sample with an ion beam, extracts particles from the surface, and measures their mass to analyze their composition. In 2024, scientists confirmed the presence of tree fern spores in sediments near the southern paleopole, proving a lush vegetation and the absence of an ice cap in this area. The presence of tree fern forests near the southern Paleocene pole shows how stably warm the planet's climate was, with a low thermal gradient between the equator and the poles. In other words, the temperature difference between equatorial and polar regions was much less pronounced than today. In this climate, many forms of life could disperse more widely. For example, primitive mammals, still small in the Paleocene, were able to explore territories once inaccessible due to the cold. The giant ferns created an ecosystem comparable to a global greenhouse, where warmth and humidity promoted lush flora. The analysis of Paleocene sedimentary rocks, in addition to the study of plants, reveals how the climate was regulated. During the Dandian, Selandian, and Thanetian, small variations in carbon dioxide occurred, influenced by geological or biological processes. For instance, organic matter buried in ocean floors could temporarily reduce atmospheric carbon, while volcanic episodes released huge amounts of greenhouse gases. In all cases, the absence of a stable polar ice cap provided the Paleocene with a homogeneous and mild climate. The Earth did not have permanent ice sheets at this time due to the planet's internal dynamics, the position of the continents, and the high level of carbon dioxide. Ocean currents, which began to organize after the geological reorganization at the end of the Cretaceous, efficiently distributed heat, preventing climate extremes and the formation of polar ice sheets. Thus, an almost uniform climate extended from the tropics to the high latitudes. Although seasonal fluctuations existed, the average annual temperature remained generally high. Isotopic studies have shown that these variations were limited, sparing Paleocene species from the extreme climate stresses we experience today. The Earth then lived under a greenhouse regime, where high levels of carbon dioxide and ocean configuration made the planet warmer and more humid. This favored abundant life on continents and in the oceans. To verify climate hypotheses, geologists study planktonic and benthic foraminifera, marine unicellular organisms that leave fossilized shells. Although not directly related to the southern paleopole, these organisms are essential for understanding variations in sea temperature and chemistry. By analyzing the isotopic composition of their shells, one can accurately trace periods of warming and cooling. This combination of analyses shows that the Paleocene was a time of stable warmth, marked by the absence of ice on the Earth's surface. Terrestrial fauna, especially mammals, occupied a warm world covered in thick forests. The tree fern forests near the southern paleopole indicate that the climate zone suitable for tropical plants extended much further south than today. These forests indicate nutrient-rich soils, promoting the growth of flowering plants and other flora typical of humid environments. Warm and humid soils encourage the rapid decomposition of organic matter, supporting a network of species, from insects to large herbivores. However, large animals were still less diversified than in the subsequent era. Paleobotanical data show that the high level of carbon dioxide favored plant growth. Since carbon dioxide is essential to photosynthesis, excess in the atmosphere stimulates plant expansion, provided that light and water are available. During the Paleocene, these conditions were met. The warmth promotes humidity and rising sea levels, resulting in considerable evaporation, fueling precipitation. Regular rain and mild temperatures create a permanent greenhouse effect, allowing thick forests to cover vast areas, including high latitudes. The climate of the Paleocene shows a warm Earth, without ice sheets and with high levels of carbon dioxide. This tropical atmosphere, extending beyond the equator, accompanies the rise of new life forms. The analysis of Delta 18O in belemnite fossils from the Danish basin shows that the surface water temperature reached about 24 degrees or 75 degrees Mars in subtropical regions. Meanwhile, the southern Paleopole, with tree ferns and dense vegetation, indicates similar conditions. Thanks to nanosims, a world with almost uniform climate is discovered without significant thermal gaps between the poles and the equator. Researchers multiply samples from sedimentary layers to better understand temperature variations. In the Danian, high thermal inertia, supported by a high concentration of carbon dioxide, limits fluctuations over a few 100,000 years. In the Selandian and Phoenician, subtle changes appear, often due to brief episodes of cooling or warming. Compared to the climate upheavals of the industrial era, these variations show relative climate stability in the Paleocene. The study of the Paleocene is not limited to historical significance. It illuminates deep climate mechanisms. Understanding how the Earth remained warm without ice sheets helps paleoclimatologists grasp the long-term consequences of high carbon dioxide content. For example, global ocean circulation redistributes heat between the equator and the poles, and the absence of ice reduces the planet's albedo, i.e., the ability to reflect sunlight. In the Paleocene, these factors helped insulate the Earth, maintaining it in a warming mode where light energy is not reflected back into space. The climate of the Paleocene, including the Danian, Selandian, and Phoenician, depicts a green and mild Earth without true ice caps. The atmosphere is rich in carbon dioxide, and subtropical seas show a surface temperature of 24 degrees or 75 degrees. Isotopic analyses, like the Delta 18O ratio of belemnites from the Danish basin, confirm this picture. Moreover, discoveries made through nanosims by studying pollen and spores from sediments near the southern Paleopole reveal forests of giant ferns, highlighting the intensity of global warming. From 66 to 56 million years ago, the Earth went through a phase of renewal, the Paleocene. During this period, the environment changed considerably, offering placental mammals a unique opportunity to develop. The continents, still in motion, created new spaces conducive to the rise of numerous species. Global temperatures remained high, creating a warm and humid climate known as greenhouse. At the start of the Paleocene, after the massive extinction of life forms at the end of the Cretaceous, placental mammals, until then limited by the dominance of dinosaurs, occupied a vast and little exploited world. The condylarths, an ancestral group of ungulate mammals, began to play various roles in the ecosystem. Their dental morphology, adapted to varied diets, contributed to the diversification of the Paleocene fauna. Alongside the condylarths, the multituberculates, an ancient group dating from the Jurassic, persisted into the Paleocene. Their name comes from the unique shape of their molars, equipped with multiple tubercles. Although they evolved over millions of years, they survived by exploiting arboreal niches to escape predators and feed on vegetation or insects. The multituberculates formed one of the longest mammalian lineages, although they were eventually supplanted by more modern rodents. In the canopies, the Plesiadapiforms, such as the genus Purgatorius, marked the beginning of a lineage leading to today's primates. These archaic primates exhibited dental adaptations and limited grasping abilities, allowing them to harvest fruits and insects in the foliage. Although they had claws rather than nails, their evolution was crucial, laying the foundation for the rise of primates. Their skeletal remains already show an orientation towards an arboreal life. After the crisis at the end of the Cretaceous, modern birds, or neorniths, rapidly diversified. Flightless birds, like some large primitive seabirds, disappeared, giving way to new actively flying lineages. These birds explored various diets and adopted lifestyles suited to the warm climate and lush vegetation. This diversity encouraged the emergence of varied reproductive and movement strategies, enriching the Paleocene ecosystem. Reptiles did not disappear, as shown by the emergence of the Sebecid crocodilians. These terrestrial predators, with elongated skulls and sharp teeth, were part of a distinct evolutionary group from modern crocodiles. According to a 2025 discovery in the Caribbean, they possessed powerful jaws adapted for hunting large prey. Their posture, closer to that of a mammalian predator than that of a modern amphibious crocodile, illustrates the adaptability of crocodilians in varied environments. Changes in terrestrial fauna are linked to the evolution of flora. The Paleocene saw the flourishing of large-leaved dicotyledonous angiosperms, creating dense and humid forests, called greenhouse forests. This term refers to the natural greenhouse effect, where high levels of carbon dioxide maintained moderate temperatures. These lush forests offered shelter and food to terrestrial animals, while barely marked seasons favored persistent vegetation year-round. Among plants, legumes became more prominent. These plants, like peas, beans, and lentils, fixed nitrogen from the air through symbioses with bacteria, enriching soils and supporting the expansion of other organisms. Their presence favored the vigor of forest ecosystems by increasing the availability of essential nutrients. Nitrogen fixation played a crucial role in soil fertility during the Paleocene. Studies of Paleocene flora revealed the presence of isoflavonoid acids in fossilized plant remains, notably in a German lignite. These chemical compounds, produced by certain plants, serve as defense against infections and herbivores. Their detection offers insights into protective and chemical communication mechanisms already present at the time. Lignite, a coal formed from partially decomposed plant debris, allows analysis of ancient chemical composition and deduction of biological interactions of the era. At the beginning of the Cenozoic, tropical forests spanned vast areas, populated by mammals searching for food on the damp ground or climbing to collect berries. Birds nested in the foliage, safe from terrestrial predators, while reptiles, from lizards to terrestrial crocodilians, roamed the banks and undergrowth. This era saw competition and the search for shelter, shaping new behaviors, stimulating species adaptation. The warm, humid climate offered abundant resources, but also required strategies to protect against high temperatures. Placental mammals stood out for their increased reproductivity compared to more archaic forms, such as monotremes or certain marsupials. The placenta, a specialized organ nourishing the embryo, allowed for better development before birth, thus increasing the survival chances of the newborns and favoring rapid expansion. This adaptive surge was manifested in condylarths, evolving into more specialized forms, and among the ancestors of modern ungulates. In this bustling landscape, survival depended on the ability to find food. Plesiadapiforms, for example, perfected their arboreal practices to seek fruits and insects in the canopy. With their agile claws, they climbed and stabilized on the branches. Fossils of Purgatorius show a skull and dentition adapted to an omnivorous diet, key to their success. The absence of large predatory dinosaurs allowed small mammals to multiply in the Paleocene forests. The cebichids, terrestrial hunting crocodilians, spread across vast insular and continental territories, as evidenced by fossils found in the Caribbean. Unlike modern crocodiles, often associated with wet zones, cebichids were better adapted for terrestrial locomotion. Their heavy skeletons and robust jaws attest to their power and specialization for capturing prey in less aquatic environments. In the Paleocene, dicotyledon angiosperms dominated the flora, characterized by their leaves with branched veins and their ability to flower. Forests, mainly consisting of broadleaf trees, thrived on the persistent warmth and humidity. Conifers, present since the Mesozoic, were relegated to cooler climates or high-altitude regions. This floral transition, with the addition of nitrogen-fixing legumes, enriched the soil and promoted plant and animal diversity. Paleobotanical studies, using pollen microscopy and chemical analysis of plant debris, reveal the co-evolution between plants and animals. The Paleocene climate was characterized by a high concentration of carbon dioxide, primarily from volcanism. This greenhouse gas trapped infrared radiation, thus warming the atmosphere and creating an overall warm environment. Some researchers estimate that the average temperature was several degrees Fahrenheit, DGF, higher than today. The absence of permanent ice caps reinforced the homogeneity of the climate, allowing forests to expand to high latitudes. Nevertheless, interspecific competition became a powerful driver of evolution. Placental mammals sought new niches: insectivores, herbivores, and carnivores. Plesiadapiforms, considered probable ancestors of primates, developed arboreal strategies. Cebichids perfected ground hunting. Neornithine birds diversified their beak shapes and nesting habits. Multituberculates, more ancient, struggled to compete with the rising rodents. These selective pressures created a landscape of innovative adaptations that would influence much of the Cenozoic. In the Paleocene, lamniform sharks dominated the oceans as major predators. These sharks, with streamlined bodies and powerful jaws, were macropredators, hunting large prey, sometimes other predators. Their hunting efficiency relied on their morphology, powerful muscles, and a sensory system capable of detecting the electric fields emitted by their prey. Present in shallow and open seas, they benefited from the void left by the disappearance of marine reptiles. They likely preyed on bony fish, cephalopods, and sometimes surviving reptiles, although their exact diet remains difficult to determine. Among the prey of large sharks in the Paleocene are teleosts, a group of bony fish that still dominate modern oceans. Their diversification, already well underway at that time, results from evolutionary innovations in the jaw, caudal fin, and internal adaptations facilitating swimming and breathing. The warm climate and warmer waters than today favored the expansion of ecological niches. The teleoasts of the era include pelagic fish in the open sea, as well as coastal forms populating emerging lagoons and reefs. Their diversity in colors, lifestyles, and reproductive strategies is notable, although preserved fossils are often limited to scales, teeth, or fragmented bones. Alongside bony fish, there are barycoid chondrichthyans, cartilaginous fish like sharks, rays, and chimeras. Barycoids are characterized by primitive traits, particularly in the shape of scales, jaws, and dorsal fins. In the Paleocene, these fish occupy various marine environments, from coastal areas to continental slopes. Fossils show medium-sized specimens with varied teeth, indicating an opportunistic diet, including small crustaceans, mollusks, and fish. They likely play a key role in the ecosystem by regulating certain prey populations. While lamniform sharks and barycoid chondrichthyans contribute to the dynamics of the Paleocene seas, another actor captures the attention of paleontologists, the giant penguin Kumimanu fordycei. Unlike modern penguins associated with polar regions, several gigantic species thrived in the southern hemisphere, notably in New Zealand. This penguin, dating back 57 million years, reached an impressive size, comparable to that of an adult human. The term Kumimanu means monster bird of the seas in Maori, and this animal is distinguished by its adaptation to deep-sea diving. With wings modified into rigid paddles and a robust skeleton, Kumimanu could perform long and deep dives to hunt large marine prey, such as fish, cephalopods, and crustaceans. This giant penguin illustrates the ability of some birds to occupy a marine niche after the disappearance of large marine reptiles. The discovery of Kumimanu fordycei around 2024-2025, widely reported in the international press, sheds light on the adaptation of marine birds over time. Paleontologists use modern techniques such as synchrotron tomography and high-precision microscopy to analyze the microstructure of bones. These methods allow the comparison of fossils with current penguins. The evolution of penguin ancestors occurs in a context of mild temperatures and vast, unexplored coastal spaces. The southern seas are ideal for their expansion, exploiting plankton, fish, and marine invertebrates, without the competition from sea lions, seals, or whales, which were not yet dominant in the Cenozoic. The marine world of the Paleocene goes beyond the large predators like sharks or giant penguins. The planktonic globigerinoid foraminifera, tiny but abundant, play a key role in the marine biosphere. These unicellular protozoa, with calcareous shells, live suspended in the water, drifting with the currents. Their scientific importance is crucial, as their fossilized shells, found in large quantities in marine sediments, provide precise records of the climate and chemistry of the oceans. The analysis of their composition allows the reconstruction of surface temperatures of the Paleocene seas, the carbon dioxide content in the atmosphere, and biological productivity. During the Paleocene, these foraminifera experience a surge, supplanting the Cretaceous lineages that had declined at the end of the previous period, illustrating their great adaptability to a changing environment. The replacement of Cretaceous lineages by new groups, such as planktonic foraminifera, results from several factors. First, the end Cretaceous extinction freed up ecological niches by eliminating many marine predators and competitors. Next, the climatic conditions of the Paleocene favor new variations in temperature and salinity, offering adaptation opportunities for organisms capable of modulating their buoyancy, reproduction, and nutrition. Finally, continental drift reshapes coasts and marine basins, creating new oceanic circulation corridors. Species that adapt quickly thrive, while others regress or disappear. The globigerinoid foraminifera are among the winners, proliferating to become dominant in the water column for much of the Cenozoic era. Fossils of planktonic foraminifera in the Daunian, Celandian, and Phoenician sedimentary layers testify to species dispersion and the increasing complexity of planktonic interactions. Scientists use modern techniques like Raman spectroscopy to analyze the mineralogical composition of shells, or synchrotron microtomography to visualize their internal structures without damaging them. These methods detect changes in the crystallization of calcium carbonate, often related to chemical variations in seawater. Planktonic foraminifera, reacting quickly to environmental fluctuations, are key indicators for paleoclimatic studies, as their populations vary according to nutrients, water temperature, and pH levels. They serve as a natural barometer to understand marine life's adaptation after the end Mesozoic crisis. The marine Paleocene also witnesses a reconfiguration of coastal ecosystems. The disappearance of Cretaceous marine reptiles and the emergence of new fish and aquatic birds reorganize food chains with increased competition for food. Although paleontological data are limited, it is likely that nutrient distribution leads to seasonal migrations. Marine species feeding on plankton, like certain pelagic fish or marine mammals, are influenced by surface productivity linked to nutrient-rich deep-water upwellings. The high temperatures and changing ocean basins of the Paleocene probably favored biodiversity hotspots, where nutrient concentrations increase the diversity and population of species. Giant penguins like Kumimanu fordycei likely find ideal fishing territories, with abundant prey and optimal diving conditions. Lamniform sharks also exploit these prey-rich areas, while teleost fish colonize new habitats. The rapid emergence of large penguins in Cenozoic history demonstrates how quickly the niches left by the extinction of marine reptiles are filled by other vertebrates, whether birds or sharp-toothed fish. This rapid change highlights the plasticity of marine life during the transition between the Cretaceous and the Cenozoic. The late Paleocene, from 66 to 56 million years, approximately 41 to 35 million miles ago, is marked by a major climatic event, the initial Paleocene-Eocene thermal maximum, which occurs at the end of this period. Just before the onset of the Eocene, the planet, still recovering from the extinction of non-avian dinosaurs, undergoes a sudden and dramatic warming. This phenomenon, key to understanding climate evolution, reveals the sensitivity of terrestrial life to atmospheric and oceanic imbalances. Through this narrative, we explore this extraordinary moment in Earth's history. When we speak of 56 million years ago, a vast and difficult to conceive time interval, we refer to an era when the continents were arranged differently. The northern hemisphere was dominated by vast tropical forests, and Antarctica was not yet covered by permanent ice. The planet, warmer and wetter, favored the development of lush ecosystems. The initial Paleocene-Eocene hyperthermal, located at the end of the Paleocene but not truly affecting the Eocene, corresponds to a rapid global warming event that occurred over several tens of thousands of years. Before this event, the Earth already experienced a warm climate, but this warming was significant enough to leave a trace in sediments and isotopic records. Ocean drilling and geological studies have revealed a characteristic chemical signature, a notable change in the carbon isotopic ratio in minerals and fossils. The term negative delta 13 carbon, or negative delta 13 carbon excursion of -3 per thousand, refers to a ratio between carbon isotopes, carbon-12, major, and carbon-13, rarer. By measuring this ratio, scientists determine the proportion of carbon-13 in a sample relative to a standard reference. A negative excursion indicates that the proportion of carbon-13 decreases relative to carbon-12. The -3 per thousand value specifies the extent of the change. This decrease suggests that a large amount of carbon-poor in carbon-13, originating from organic sources or volcanic processes, was rapidly released into the atmosphere and oceans. One of the main hypotheses to explain the massive carbon release at the onset of the Eocene is the destabilization of oceanic methane hydrates. These solid structures, formed in marine sediments at low temperature and high pressure, would trap methane in cages of frozen water. If the reservoir warms, or if the pressure changes, the hydrates decompose and release methane, a potent greenhouse gas, thus contributing to global warming. This methane, with a low carbon-13 content, corresponds to the isotopic fingerprint measured in the Upper Paleocene sediments. Other theories, such as intense volcanism or the decomposition of organic matter in swamps, are also being studied to better understand the mechanisms of the initial Paleocene-Eocene hyperthermal. Alongside the isotopic excursion, researchers observed a notable enrichment in mercury in the clays of the period. Mercury, often associated with volcanic activity, is released into the atmosphere during major eruptions and subsequently deposited in sediments. A higher mercury level may indicate an intense volcanic phase. The correlation between this enrichment and the drop in delta-13 carbon suggests that volcanism likely contributed to the abrupt warming, either by releasing methane or by adding carbon dioxide, or by combining these two processes. This synchronicity reinforces the hypothesis that volcanism played a role in injecting large quantities of light carbon into the atmosphere. The rapid warming of the Paleocene had major consequences on ecosystems. Although temperatures were already high, this heat peak further increased surface temperatures, reaching up to sometimes 24 degrees Celsius or 75 degrees Celsius in some subtropical regions. This warming intensified rainfall episodes in some areas, while others experienced increased evaporation, causing water stress. Studies of pollens and fern spores near the South Pole show that plants were adapting to these high temperatures. Tree fern forests thrived further south, indicating that the high latitudes were without permanent ice. The Paleocene hyperthermal event led to rapid changes in the distribution of species and sometimes the size of certain animal lineages. Mammals, for example, moved to higher areas or further from the equator in search of more favorable conditions. Temperature, influencing access to food and physiology, can also cause a shrinkage of species, a phenomenon known as transient dwarfism. Marine drilling also shows a replacement of oceanic plankton, with some foraminifera species being replaced by others better adapted to warmer and more carbon dioxide-rich waters. Although it occurred several tens of millions of years ago, the initial Paleocene-Eocene hyperthermal is of interest to scientists because it reveals the sensitivity of the climate. The rapid injection of carbon into the atmosphere, leading to global warming, serves as a natural model compared to our current era. marked by the massive emission of carbon dioxide and other greenhouse gases. Carbon isotopes allow scientists to trace the origin of this additional carbon and analyze the climatic response, while mercury provides an additional clue about the volcanic activity of the time. The Paleocene-Eocene hyperthermal, which lasted a few 100,000 years at the end of the Paleocene, precedes the official beginning of the Eocene. Although its name connects the Paleocene and the Eocene, most researchers believe it rather marks a transition toward the Eocene thermal maximum. Difficult to distinguish precisely from the beginning of the Eocene, this event is often described as the final warm phase of the Paleocene, foreshadowing the even more pronounced Eocene thermal optimum on a global scale. This sudden warming caused significant changes in the biogeochemical cycles, involving the exchange of materials and energy between the biosphere, hydrosphere, atmosphere, and lithosphere. Modern research has revealed various clues in the clay layers, isotopic changes in carbon, mercury enrichment, and in some regions, variations in ocean salinity. Corals sometimes suffered from bleaching, although reefs were less developed than they would be later. Planktonic microorganisms, the basis of the marine food chain, showed morphological changes in response to water temperature and ocean acidification. The warming allowed for new species migrations between continents, thanks to terrestrial corridors accessible at high latitudes. It favored the expansion of forest ecosystems, allowing some mammals to extend their range. At the end of the Paleocene, new lineages of placental mammals, including the ancestors of primates and ungulates, appeared. These lineages would diversify widely during the Eocene, as shown by fossils found in deposits from this intense climatic transition period. Although the hyperthermal episode is clearly identified in geological records, its exact cause remains debated. Scientists agree on the combination of several factors, such as the injection of organic or volcanic carbon and the oxidation of sediment rich in plant matter. Volcanism, with the abundance of mercury in the deposits, plays a key role in the rapid warming. Climate models still encounter uncertainties, particularly concerning the speed of methane release and how ocean currents distributed heat around the globe. This phenomenon remains at the center of much research, using various approaches: high-resolution stratigraphy, astrochronology, isotopic analyses, and microscopic studies of fossils. During the Eocene, the Earth underwent a remarkable transformation. This period is divided into four main subdivisions: the Epresian, beginning of the Eocene, the Lutetian, middle, the Bartonian, second part, and the Priabonian, end of the Eocene. To understand paleogeographic changes, imagine a moving puzzle where continental plates move slowly, shaping oceans and emerging lands. At that time, the Western Tethys Basin played a key role, gradually closing due to tectonic movements, bringing Africa, Eurasia, and some continental fragments closer together. The Western Tethys Basin, named after an ancient sea separating two large continental blocks, was much larger during the Eocene. However, at this time, it remained a reduced portion due to the convergence of tectonic plates, particularly Africa and Eurasia, which gradually narrowed this maritime space. The progressive closure meant that the distance between the lands surrounding the sea slowly decreased. Once, the Tethys Ocean connected the future Mediterranean with southern Asia. During the Eocene, the western portion of this ocean shrank, heralding the formation of modern Mediterranean basins and nascent alpine ranges, with saltwater retreating to reveal new shores and allowing mountains to rise. Parallel to the closing of the Tethys Basin, the nascent collision between India and Asia occurs toward the center of the Eurasian plate. This ongoing plate convergence culminates around 50 million years ago. During the Eocene, the Indian plate, once separated from the Gondwanaland block, rapidly drifts northward at a speed of up to 10 centimeters or 4 inches per year, an exceptionally fast movement on a geological scale. Although described as nascent, this collision initiates the slow but inevitable rise of colossal mountains. At the same time, the North Sea reaches its peak of extension, widely covering the lands between continental Europe and Scandinavia. In the Eocene, this marine zone inundates vast plains, much of northern Europe. The sediments found bear witness to the abundance of marine organisms and aquatic flora, characteristic of a relatively warm climate for these latitudes. The Eocene climate, milder than today, fosters the proliferation of temperate and subtropical forests. The marine expansion in northern Europe also contributed to the formation of rich sedimentary basins. Another significant change in Eocene paleogeography occurs around the Caribbean with the emergence of the Aves Ridge. This ridge refers to an elevated underwater structure, which, over the Eocene, becomes emergent. That is, it rises above sea level to form land masses. This uplift may have been favored by tectonic processes, particularly plate convergence or changes in the expansion of neighboring oceanic ridges. This phenomenon can be visualized as a vast underwater uplift, slowly becoming an island or archipelago. The geological remnants of the Aves Ridge, studied by drilling or seismic surveys at sea, reveal a complex past marked by volcanic rocks, marine sediments, and episodes of magmatic activity followed by marine deposits before the final emergence. The various geological movements of the Eocene are not mere chance. They participate in a global rearrangement that shapes the future continental configurations of the Cenozoic era. The disappearance of the Tethys Ocean and the birth of new mountain ranges in Eurasia alter atmospheric flows and terrestrial migrations. At the same time, rising waters transform northern Europe's coastlines, creating specific littoral ecosystems in the North Sea. In the Caribbean, the uplift of the Aves Ridge changes local ocean circulation and creates new corridors for marine migrations. To reconstruct the paleogeographies of the Eocene, researchers use various methods. They compare the sedimentary sequences of the alpine ranges formed during the Tethys closure and analyze the chemical signatures of plankton microfossils. The shells of foraminifera, for example, reveal the temperature and salinity of ancient waters. For the Aves Ridge, scientists use bathymetric maps and core samples to estimate the periods of emergence, while radiometric dating on volcanic rocks determines the exact time of uplift. Finally, the study of the India-Asia collision relies on geological data from the Himalayas, where traces of the ocean that once separated the two plates are found. The gradual reshaping of marine and terrestrial spaces significantly influences the climates of the time. The distribution of land and seas largely determines the circulation of ocean currents and air masses. In the Eocene, the Earth benefits from an overall warm climate. However, tectonic movements can isolate marine basins or open new oceanic passages, thus altering heat transfers. The closure of the Western Tethys, for instance, sets the stage for the formation of future maritime corridors toward the Atlantic or Indian Ocean. The India-Asia collision also initiates the slow elevation of the Himalayas, influencing monsoon circulations in Asia. In the north of Europe, the expansion of the North Sea during the Eocene leads to the formation of wetlands, coastal marshes, and a productive deltaic ecosystem. The fine sediments rich in organic matter preserve the remains of mollusks, crustaceans, and fish that thrive in this shallow environment. The warmth of these latitudes promotes dense vegetation, with floodplains and coastal wetland forests. These environments lead to the accumulation of plant debris, which transform into coal or other carbonaceous formations. The imprint of this marine extension is found in the deep geology and in the fossil vegetation. Crossing the Atlantic to the Caribbean, one observes, during the Eocene, the emergence of the Aves Plateau. This landmass may create obstacles that favor the diversification of certain marine species by separating populations of corals or mollusks. The emergence of this shoal also allows the establishment of terrestrial plants, coastal birds, and reptiles seeking new territories. Although details on the colonization of the Aves Plateau are limited, this tectonic uplift likely served as a bridge for the dispersion of species between Central and South America. The subduction of the oceanic plate under Asia, associated with the friction of the Indian plate, releases a substantial amount of tectonic energy, raising mountains and altering the regional topography. Although during the Eocene, we only see the beginnings of the future Himalayan chain, the uplift of landforms already has climatic and paleogeographic repercussions. As India penetrates Asia, the Eocene seas get reduced, and the sediments in basins like those in Pakistan and Tibet change. Current studies based on drilled samples reveal the history of this Eocene sea crushed between the plates. The closure of the Western Tethys Basin will later lead to the birth of the Mediterranean and Black Sea, heirs to the remnants of this ocean. Throughout the Eocene, this basin contracts due to the convergence of Africa, Eurasia, and other continental microblocks. This closure is not uniform. It creates residual microbasins and tongues of seas encircled by emerging reliefs. In these environments, marine life is trapped, evolving under changing salinity conditions, while terrestrial fauna and flora colonize the newly emerged shores. In the Apresian, Lutetian, Bartonian, and Priabonian, major geological trends emerge. The Tethys Ocean narrows, India collides with Asia, the North Sea expands, and the Aves Plateau emerges. These processes, taking place over millions of years, deeply sculpt the face of the Earth. The Eocene thus marks a key chapter in the formation of landforms, the distribution of seas, and the emergence of new migration routes for fauna. These transformations redefine the map of the planet, setting the stage for future tectonic episodes and climatic changes to come. The Eocene, spanning approximately 56 million to 34 million years ago, is marked by an extraordinary trigger, the early Eocene climatic optimum. This phenomenon, also called the early Eocene climatic optimum, is characterized by high global temperatures and surprising environmental conditions, difficult to imagine in our current climate. This narrative explores this unique period, emphasizing the intense heat, the scientific evidence that reconstructs this climate, and the remarkable presence of palm forests as far as latitudes close to the poles. During the Eocene, the drift of continents and the evolution of fauna and flora continue at a sustained pace, but it is the climate that particularly marks the early Eocene climatic optimum. The Earth was generally warmer, without permanent ice caps at the poles. Ocean surface temperatures reached about 30 degrees or 86 degrees Celsius at temperate latitudes, such as at 40 degrees north latitude. Imagine an almost tropical ocean stretching over thousands of miles, bathing coasts covered with dense forests. To understand how researchers determine temperatures of 30 degrees or 86 degrees F in these regions, we need to examine fossils and isotopic chemistry. In marine sediments, remains of marine animals, including microfossils like foraminifera, as well as remains of fish and sharks, bear evidence of past conditions. Scientists studied fossilized teeth of sharks of the genus Otodus, found in layers of the Euprasian in Morocco, to reconstruct ocean temperatures of that era. On the fossil teeth, researchers measure an indicator called delta-18 oxygen, which reflects the ratio between oxygen-18 isotopes captured in the minerals of shark teeth. This indicator is essential in paleoclimatology. Indeed, the proportion of these isotopes varies with the temperature of the water in which the animal lived. The higher the temperature, the lower the concentration of isotope 18. Thus, by analyzing the chemistry of fossil teeth, geologists and paleontologists can estimate the temperature of the water in which these sharks evolved millions of years ago. With advanced spectrometry measurements in the laboratory, researchers estimated that at 40 Yzdegrium or 24 miles north latitude, the surface water temperature during the early Eocene reached approximately 30 degrees Celsius or 86 degrees Celsius, almost that of current tropical waters near the equator. This anomaly is due to several factors, primarily the increase of carbon dioxide in the atmosphere. During the early Eocene climatic optimum, the carbon dioxide concentration reached about 1,500 parts per million, compared to a little over 400 today, a much lower level than that of the Eocene. Carbon dioxide, or carbonic gas, is a greenhouse gas that traps heat in the atmosphere. In large quantities, it promotes high temperature as it reflects infrared radiation back to the Earth's surface instead of letting it escape into space. This high concentration of carbon dioxide at the time is explained by several factors: volcanic activity, tectonic movements altering continents, and perhaps the decomposition of organic matter. This occurred on a planet already warm after the late Paleocene crisis, which wiped out non-avian dinosaurs. A fascinating aspect of the early Eocene climatic optimum is the discovery of palm forests at very high latitudes. The most emblematic case is that of Svalbard, an archipelago beyond the Arctic Circle. The fossils found show the presence of palms and other tropical and subtropical plants, as well as organisms usually living in warmer climates. This indicates that at that time, the average annual temperature in these polar regions was high enough to allow the growth of tropical vegetation. The annual averages could be around 10 to 15 degrees Celsius or 50 to 59 degrees, with hotter summers and less harsh polar nights than today. This surprising situation in polar regions raises questions about the distribution of fauna. Imagine a traveler roaming the Earth at that time. As they progressed from south to north, they would not have met the marked climatic transitions we know today. The temperate zones resembled the current tropical and subtropical belts. Closer to the poles, they would have found a warm and humid environment, rich in forests and lush vegetation, with palms, ferns, and a fauna of insects and birds. The temperature gap between low and high latitudes was much smaller, a phenomenon due to the enhanced greenhouse effect. Imagine this warm seawater, ideal for abundant marine fauna, from extinct ammonites to giant sharks. Corals would likely thrive in many marine basins, although their reefs sometimes differed from current ones. Ocean circulation was also different. A warmer Earth has less pronounced thermal gradients between the equator and the poles, which modified ocean currents. Tropical waters extended further north, warming the atmosphere at mid-latitudes and pushing tropical vegetation up to near the polar circles. To evaluate the impact of this warming, paleontologists examine how flora and fauna adapted. On land, plants from warm climates moved northward, taking advantage of mild temperatures and abundance. At sea, fish, sharks, and other marine groups expanded their territory thanks to the reduced temperature gap between tropical and temperate waters. This expansion altered the balance of ecosystems, favoring certain predators and prey. Moreover, this heat influences the chemistry of the oceans, particularly the solubility of oxygen and planktonic life. Geological records are essential to decode a past almost unreal compared to the current climate. Sedimentary layers, rich in marine and terrestrial fossils, form a book that paleontologists and geologists slowly decipher, layer by layer. They spend years analyzing, dating, and comparing clues to reconstruct the most accurate picture possible of this vanished world. For example, Otodus shark teeth from Morocco, dating from the Ypresian, serve as markers. The delta-18 oxygen isotopic signal in these teeth allows for evaluating past marine temperatures. Coupled with other data on carbon dioxide and plant fossils, these pieces of information help reconstruct the global puzzle. This period of extreme heat with lush vegetation extending to high latitudes favored the evolution of many species, including our mammal ancestors. A warm and humid climate enables extensive arboreal life, vast rainforests, and easy access to food. Fossils show a proliferation of new mammals, birds, and reptiles in the northern hemisphere. Meanwhile, marine ecosystems housed rays, various bony fish, and many sharks, occupying diverse ecological niches. Behind the term optimum, ambiguity remains. What is favorable for some groups of organisms is not necessarily so for all. The Earth, although lush, was not a paradise. High temperatures and the high concentration of carbon dioxide can lead to ocean acidification and rapid upheaval. Each major ecological change involves winners and losers, but for species adapted to tropical or subtropical climates, this widespread heat opened new opportunities for dispersion. Over time, the Eocene saw extreme temperatures decrease. Natural mechanisms such as rock weathering absorbing carbon dioxide and the reconfiguration of ocean currents led to gradual cooling. Although this episode of intense heat lasted only a few million years on a geological scale, it offered a diverse environment for living species in the short term. The early Eocene climate optimum highlights Earth's climatic flexibility. In the north, palm forests on the Svalbard archipelago showed how the Arctic was turning into an exotic garden. This phenomenon demonstrates life's ability to adapt to significant climate variations, provided there is time to evolve or migrate. The early Eocene climate optimum plunges us into a world where temperatures reached 30 degrees Celsius or 86 degrees Fahrenheit at latitudes currently temperate, and where palm trees would thrive up to 70 degrees north latitude. This era reveals Earth's climatic flexibility, demonstrating that in a few million years, or due to tectonic changes, climate zones can be radically redefined. The Eocene teaches us about the constant dynamics of Earth and the impact of carbon dioxide on climate. Shark otodus teeth from Morocco and Arctic rainforests illustrate a climatic optimum where Earth was much warmer, with temperatures almost like tropical seas. This unique episode of the early Eocene, marked by intense heat, offers us a fascinating glimpse of a world where life thrives in unexpected conditions, bathed by an atmosphere rich in carbon dioxide. During the Eocene, the ocean saw the emergence of a fascinating diversity of life forms. including the ancestors of whales and the archaic cetaceans. These primitive marine mammals, still close to their terrestrial ancestors, exhibit transitional characteristics that provide paleontologists with valuable insights into cetacean evolution. Among the archaic cetaceans, Basilosaurus stands out due to its impressive size, measuring up to 18 meters or 59 feet long, and its serpentine body. Although its name means king lizard, it was actually a marine mammal, dominating the Eocene food chain. Its atrophied hind limbs bear witness to its transition from a quadrupedal ancestor towards aquatic locomotion. Another representative, Dorudon, smaller at about 5 meters or 16 feet, shares characteristics with Basilosaurus, such as an elongated skull and conical teeth, but presents a more compact and hydrodynamic silhouette, foreshadowing the forms of modern cetaceans. Aside from marine mammals, the Eocene saw the emergence of a wide diversity of fish. Otoliths, small calcified structures in the inner ear of fish, are valuable clues for identifying fossil species. Thanks to them, clupeiform fishes, related to modern herrings and sardines, have been discovered. These fishes, with fusiform bodies and silvery scales, played a crucial role in the marine ecosystem, serving as a link between plankton and large predators like the archaic cetaceans. Another significant phenomenon of the Eocene is the resurgence of coral reefs. After the Cretaceous crisis that had disrupted marine ecosystems, corals recolonized the tropical zones thanks to warm, shallow waters. These reefs, veritable havens of biodiversity, provided shelter, food, and breeding sites for numerous organisms, from invertebrates to fish. They thus created marine oases of life. The site of Wadi al-Hitan in Egypt, dubbed the Valley of the Whales, is a key location for the archaic marine fauna of the Eocene. Numerous fossils of primitive cetaceans from the early Eocene, a crucial stage in the evolution of marine mammals, have been discovered there. The skeletons found reveal the adaptation of archaic cetaceans to aquatic life, while retaining traits of their terrestrial ancestors. Today, this desert site is a geological archive of inestimable scientific and historical value. It tells the story of a marine basin in full transformation towards a fully marine mode of life. The late Eocene does not mark the end of archaic whales, as shown by a discovery in 2025 in Charleston, United States. This site revealed fossils of 25 cetacean species of the Oligocene, precursors of late Eocene lineages. Although these fossils mostly belong to the following period, they testify to the evolutionary continuity between the Eocene archaic cetaceans and modern whales. Charleston on the North American coast is a key site that offers a valuable view of the transition between the Eocene and Oligocene, and on the diversity of archaic whales of this pivotal era. Studying these discoveries gives a sense of the anatomical transformations that have marked the evolution of whales from their terrestrial quadrupedal ancestors. At first, they still moved with functional hind limbs and did not yet have the caudal propulsion of modern cetaceans. Gradually, their hind limbs atrophied, their nasal opening moved back to the top of their skull, and their tail became a key element for fast swimming and hunting. This long evolutionary process, initiated long before the Eocene, found a favorable ground in a warm climate and ecosystems conducive to diversification. The Eocene Sea became a laboratory of experimentation, where different groups of vertebrates explored new opportunities. Clupeiform fishes benefited from abundant plankton, coral reefs regained their past richness, and archaic cetaceans conquered the oceans. Basilosaurus and Dorudon are only two examples of a broader radiation, with other less known but equally representative species of the evolutionary potential of the time. Paleontologists aim to trace the links between these lineages using advanced methods like skeletal analysis, X-ray microtomography, and the study of stable isotopes in fossil teeth. Their goal is to reconstruct Eocene marine fauna and to understand the factors influencing these adaptations. The climate plays a key role in these developments. At the time, surface waters were warmer than they are today, particularly in equatorial and subtropical regions. This temperature, combined with higher carbon dioxide levels, stimulates the biological productivity of the oceans. Corals, sensitive to specific environmental conditions, took advantage of the opportunity to expand into areas that later cooled down. Fish, such as clupeiforms, thrived and dispersed. Archaeocetes, on the other hand, took advantage of calm seas and extensive coastlines to explore different strategies of movement and hunting. The study of fish otoliths from the Eocene adds an essential dimension to the understanding of that time. These small balanced stones, present in the inner ear of fish, retain valuable information about their environment, such as salinity, temperature, and nutrient availability. The analysis of otoliths allows for the reconstruction of fluctuations in these parameters and provides a more precise picture of the Eocene ecosystem. Clupeiforms, sensitive to these variations, are particularly revealing. Their fossils, along with their otoliths, offer crucial clues for understanding the structure of trophic networks and seasonal migrations of this distant period. The return of coral reefs also influences the distribution of many other marine species. By forming vast calcareous structures with their skeletons, corals create a complex and three-dimensional habitat. Within their crevices, many organisms find refuge, hide from predators, or raise their young. Thus, archaeocetes can take advantage of this diverse environment to evolve and thrive. Since the beginning of the Eocene, about 56 million years ago, the Earth has been going through a period of profound changes. This epoch, divided into 4 successive periods, sees the continents continuing their movement in a globally warm and humid climate. Lush forests dominate the plant landscape, while terrestrial fauna develops new forms and behaviors. This gives rise to species that herald the current diversity of mammals, birds, and other terrestrial groups. In this narrative, we explore this fascinating era, discovering how primitive primates, large ungulates, and even a giant bird inhabited a transforming environment. We will also see the rise of equatorial rainforests and the growth of the first grasses, which begin to spread in certain environments. The Eocene is marked by a warm climate conducive to the expansion of tropical ecosystems. The vegetation is lush, with dense and diverse forests that harbor a varied fauna. Although the extinction of large non-avian reptiles at the end of the Cretaceous upheaved ecosystems, some reptiles persisted. The expansion of placental mammals and the diversification of birds, some of which reach impressive sizes, characterize this epoch. Around 42 million years ago in Texas, the fossilized skull of a primitive primate was discovered in the region dubbed the Devil's Graveyard. It belongs to the suborder of haplorhines, which includes modern monkeys and tarsiers. This fossil reveals features close to more evolved primates, particularly at the level of the frontal bone. Thanks to 3D scanners, scientists have been able to examine the shape of the skull, the position of the orbits, and the dentition. This discovery is part of a diversity of primitive species that populated trees and fed on fruits, leaves, and insects in a rich forest environment. The discovery of this primate shed light on the origin and evolution of haplorhines during the Eocene. At that time, North America was connected to Eurasia by land bridges, allowing for the dispersion of primates into various forest environments, favored by a mild climate and abundant vegetation. The study of the skull reveals internal structures close to more evolved primates, highlighting the transition to forms similar to modern monkeys. These fossils confirm that the Eocene was a period of morphological innovations, where lineages evolved to adapt to varied environments. The Eocene marks the rise of ungulates, notably the perissodactyls and artiodactyls. The perissodactyls, like modern horses and rhinoceroses, have an odd number of toes, while the artiodactyls, like deer and cattle, have an even number. Among the Eocene perissodactyls, Coryphodon stands out as a large, heavy mammal, resembling a robust hippopotamus. Its diet, based on tough leaves and moist vegetation, underscores the richness of the terrestrial ecosystems of the time, already populated by large herbivores, well before the appearance of modern forms. The Eocene artiodactyls, such as Diacodexis, were more slender. Considered one of the first artiodactyls, Diacodexis had thin limbs adapted for running and probably lived in forested and semi-open environments. Its diet, consisting of tender leaves, shoots, and fruits, reveals its ability to adapt to the lush Eocene environment. The coexistence of large herbivores like Coryphodon and agile small artiodactyls shows that the Eocene offers a diversity of ecological niches. In the avian world, the Eocene is equally full of surprises. It is, in fact, during this period that we find traces of large, flightless birds. Diatryma, a giant bird of the Eocene, measured over 2 meters or about 7 feet in height and lived in the forests and swamps of the time. Although unable to fly, it was a predator or scavenger, probably feeding on vegetation, small animals, or carrion. The more complete fossils found in 2025, including an almost intact skull, have provided better insights into its anatomy. This reconstruction revealed details about the shape of its beak, the strength of its jaw, and its muscle structure, offering a better view of its dietary and behavioral capabilities. Diatryma illustrates the spectacular diversification of birds after the extinction of non-avian dinosaurs. At that time, birds occupied a variety of ecological niches, whether in aquatic, forest, or terrestrial environments. Diatryma managed to establish itself in spaces unusual for birds, benefiting from the absence of large terrestrial predators. This adaptation, seen in other bird groups from the Eocene, reflects the rise of new avian forms that thrived after the Great Cretaceous extinction. The abundance of terrestrial fauna during the Eocene is closely linked to flora, especially the equatorial rainforests that developed widely, notably in Amazonia. The analysis of fossil pollen dating back about 50 million years reveals plants typical of tropical environments: heat, humidity, and abundant rainfall. The stomata of leaves indicate a high humidity characteristic of rainforests. These dense forests provided an ideal refuge for many animals, including primates, by offering a canopy rich in fruits and foliage, conducive to their diet and survival. During the Eocene, the first C3 photosynthesis grasses emerged. C3 photosynthesis is a chemical process where carbon dioxide is fixed to produce sugars. These grasses, including many Poaceae, began to develop, marking an important step in plant diversification. Although they did not yet occupy large areas, as they would later in the Oligocene or Miocene, their presence, identified by fossil pollen, indicates the emergence of grasslands and the diversification of developing ecosystems at this time. The expansion of ecological niches during the Eocene profoundly influenced the fauna. Herbivorous mammals like Coryphodon benefited from the proliferation of foliage and grasses, while small artiodactyls, such as Diacodexis, fed on young shoots. Primitive primates found fruits and seeds in the dense canopy, and giant birds fed on ground-level vegetation and fallen fruits. In this mild climate, with temperatures around 25 to 30 degrees C or 77 to 86 degrees, the diversity of animal and plant species developed rapidly, thanks to an environment favorable to both fauna and flora. The recent discoveries about Diatryma, notably the complete skull published in 2025, reveal the robustness and imposing size of this bird. The analyses of the base of the skull have allowed the formulation of hypotheses about the strength of its beak and how it fed. Although the diet remains debated, some researchers believe it was primarily herbivorous or frugivorous, while others consider that it also consumed weakened animals or carcasses. The relative absence of large mammalian predators in certain regions of the Eocene likely allowed such birds to thrive, exploiting ground resources without the threat of major carnivores, which would not emerge until later. Revisiting the history of the primate nicknamed the primate of the Devil's Graveyard, as well as species like Coryphodon, Diacodexis, and the bird Diatryma, allows us to better understand the evolutionary dynamics of the Cenozoic. The Eocene marks the emergence of cranial features in primitive primates, but also the consolidation of large herbivores in the terrestrial food chain. The latter, benefiting from new resources such as equatorial forests and the first C3 grasses, diversified their ecological strategies. Some adapted to arboreal life, while others specialized in certain types of plants, and Diatryma asserted dominance on the forest floor. Advances in paleontology, notably tomography and chemical analysis of fossils, allow an increasingly precise reconstruction of the anatomy and lifestyles of these extinct creatures. This diversity of species, both in America and elsewhere, reflects the geographical changes that were shaping the Eocene. The movements of tectonic plates and the variations of the seas modified terrestrial corridors, favoring the isolation or dispersion of populations. For example, Eocene primates could travel to Eurasia via northern routes, while some ungulates remained confined to more restricted areas. These spatial dynamics influence the ecological roles of species. The study of fossil teeth provides crucial information about the region of origin of animals and their diet, indicating that rainforests rich in vegetation favored the development of teeth adapted for chewing plant material. The Eocene marks a decisive stage in the evolution of terrestrial life. We see the emergence of large herbivores, the first primates close to modern apes, and strange giant birds that are now extinct. The equatorial forests, humid and warm, offered a refuge to a multitude of opportunistic species. Innovations abound. Primates developed a larger brain, artiodactyls adapted to running, and some birds, equipped with powerful beaks, explored the resources of the undergrowth. It was an era of biological explosion, which fossils still allow us to contemplate. Between the Epresian and the Pre-Ebonian, Earth presented a very different face than today. The mild temperatures, often around 25 to 30 degrees C or 77 to 86 degrees C, favored a lush vegetation. Thanks to advances in high-resolution imaging and chemical analysis of fossils, researchers can now explore these ecosystems with unprecedented precision. From the tiny ear bone of a primate to the large legs of a running bird, every detail is accessible. The Eocene shows that terrestrial life, long relegated after the era of great reptiles, was already in full swing. Archaic primates with evolved skulls, ungulates with varied diets, and giant birds illustrate the inventiveness of evolution in a warm and changing world. This era marks a turning point, dense forests became the stage for new adaptations, more complex feeding behaviors, and increased competition. By exploring this ancient life, we discover the deep roots of many current species, stemming from the rich ecosystems of the Eocene. Ultimately, evoking the precursor primate of Devil's Graveyard, Coryphodon diacodexis or Diatryma, is to celebrate the richness of a bygone but foundational world. Each discovery brings us closer to understanding the drivers of terrestrial biodiversity. They also testify to the remarkable resilience of life in the face of climatic and geological upheavals, since only a few million years elapsed between the end of the dinosaurs and the complexification of mammalian ecosystems. In this short period, nature reinvented forms and behaviors, leaving fossil traces that allow scientists to reconstruct this fascinating evolutionary adventure. The transition between the Middle Eocene and the Late Eocene, spanning from 56 to 34 million years ago, marks a period of gradual cooling on Earth. This period, though subtle, presents important geological indicators, such as the evolution of the strontium isotope. This isotope, present in the oceans, reflects tectonic activity and the weathering of continents. During this transitional phase, a gradual increase in strontium values signals not only climate change, but also a reorganization of water mass circulation. This prepares the planet for more marked transformations during the Oligocene. The gradual cooling of the climate does not yet mean a frozen Earth, but it signals a decisive turning point. It is during this time that Antarctica begins to be covered with ice. Sediment cores and drillings reveal a growing formation of ice caps in the high southern latitudes. This process marks the beginning of Antarctic glaciation, which will have a lasting impact on ocean currents, oceanic ecosystems, and sea levels. The nascent glaciation does not yet transform the landscapes of the late Eocene. In warm regions, palm trees and humid forests are still present, as is a varied fauna. Elsewhere, vegetation begins to change, influenced by the drop in temperatures. Mammals continue their diversification, but this cooling initiates adaptations in some lineages that will mark future times. Around 34 million years ago, a key stage occurs: the transition from the Eocene to the Oligocene. This marks a lasting cooling of the climate and the expansion of ice in Antarctica. Without going into the details of this new era, let us remember that this shift initiates the creation of new environments where life continues its evolution and diversification. At the beginning of the Oligocene, between 34 and 23 million years ago, the Earth undergoes significant tectonic changes. The continental plates, which form the Earth's crust, continue to move under the effect of convection currents in the Earth's mantle. The Oligocene is divided into two major periods: the Rupelian, from 34 to 29 million years ago, and the Chattian, from 29 to 23 million years ago. These tectonic transformations will reshape the contours of the oceans and influence the evolution of species. During this period, major events mark the reconfiguration of the oceans and continents. The Tasman Sea forms, Australia gradually becomes isolated, and the opening of the Drake Passage between South America and Antarctica gives birth to the Antarctic Circumpolar Current. Furthermore, Africa begins its slow migration towards Eurasia, marking a turning point in the planet's geography. Before the Oligocene, Australia remained close to Antarctica, although in the process of separating since the end of the Cretaceous. It was then part of the supercontinent Gondwana, alongside Antarctica, Africa, South America, and India. At the beginning of the Oligocene, the break between Australia and Antarctica completes, driven by tectonic movements. The opening of new seabeds to the south gives rise to the Tasman Sea, altering ocean currents and climate. This growing isolation also transforms terrestrial fauna. Marsupials and monotremes evolve separately in a unique ecosystem. In parallel, the opening of the Drake Passage between Tierra del Fuego and the Antarctic Peninsula plays a key role in the geography of the Oligocene. Before this period, Antarctica remained connected to South America, but tectonic movements eventually create a gap where the ocean infiltrates, opening a maritime passage. This strait then allows the circumpolar current to form, thermally isolating Antarctica. This cold current, by encircling the continent, promotes the extension of ice and lowers temperatures throughout the southern hemisphere, with a global impact on the climate. The Antarctic circumpolar current is essential for understanding the evolution of the climate during the Oligocene. Before the opening of the Drake Passage, warm waters from tropical zones more easily reached Antarctica, thus softening its climate. However, after this passage opened, an ocean current was able to circulate around Antarctica, creating a natural thermal barrier. This change isolated Antarctica, promoting the expansion of glaciers and a notable drop in temperatures. This progressive cooling initiated a colder climate that would influence the continent's evolution for millions of years. This dynamic led to the formation of ice sheets that would define Antarctica's geography. To understand these events, it's necessary to return to the functioning of tectonic plates. The Earth consists of a solid crust, a warm and moving mantle, and an internal and external core. The plates float on the asthenosphere, the upper layer of the mantle, and move a few centimeters or inches per year. In the case of Australia, geological data show a rapid separation from Antarctica, forming the Tasman Sea. Similarly, the Drake Passage opens between Antarctica and South America. These slow movements, spread over millions of years, profoundly reshape the surface of the planet. During the Rupelian and Chattian, climatic and tectonic changes deeply affected the fauna and flora. Isolated after its separation from Antarctica, Australia became a sanctuary for marsupials, which evolved without competition, developing unique reproductive strategies. Meanwhile, Antarctica became increasingly isolated by glaciers and the cold climate, reducing terrestrial habitats. The opening of the Drake Passage also played a key role in biogeographic fragmentation, creating marine barriers that separated populations, leading to new lineages. Australia, with its drier and temperate climate, saw the emergence of unique flora, adapted to these conditions. During the Oligocene, Africa began its migration towards Eurasia, a movement that would continue into the Miocene. Still isolated at the time, bordered to the north by the Tethys Ocean, it drifted slowly northeast. This progression would later lead to major tectonic collisions, giving rise to mountain ranges such as the Alps and the Atlas. For now, the contact had not yet occurred, but the Tethys Ocean was shrinking, largely due to subductions. This closure would soon redefine the geography of the Mediterranean basin. Faunally, exchanges remained limited, although some species began to use emerging islands or corridors. The Oligocene marks a major turning point in the configuration of continents, especially in the southern hemisphere. The formation of the Tasman Sea and the opening of the Drake Passage clearly defined the isolation of Australia and Antarctica. This division altered ocean circulation, creating the Antarctic circumpolar current, which regulates the temperature and salinity of the oceans. The end of the Oligocene saw the first expansions of ice sheets in Antarctica, affecting the global climate. and leading to a gradual cooling of marine and terrestrial biomes. Polar regions became more hostile, favoring species adapted to the cold, while the tropics maintained a flourishing biodiversity. To understand these major upheavals, researchers rely on modern tools. The study of rock magnetism allows tracing the past movements of continents. In the seabed near the Tasman Sea, or the Drake Passage, sediment cores reveal the stages of these basins' openings. These data are cross-referenced with underwater mapping and marine fossils to establish a precise chronology. There, we observe species that gradually stop mixing, proof of the increasing isolation between oceans. The continents continue their drift, and Antarctica gradually isolates itself. This movement triggers the appearance of specific ocean currents and favors the expansion of the ice sheet. In parallel, the global temperature drops, heralding a shift towards a colder and more stable climate. By the end of this period, permanent ice first settles at the South Pole. The Oligocene thus initiates the great climatic balances that will influence the rest of Earth's history. A major indicator of climate cooling is the delta-18 oxygen, measured in the shells of foraminifera. Their skeleton records the seawater composition of their time. During glaciations, water retained as ice makes the oceans richer in heavy oxygen isotopes. This concentration then increases, signaling the expansion of the Antarctic ice sheets. In the Oligocene, this marker clearly shows the establishment of a polar climate. It remains a reference today for tracing major past climate variations. In addition to the rise in delta-18 oxygen, there is a gradual decrease in atmospheric carbon dioxide. At the beginning of the Oligocene, it exceeded 800 ppm, but dropped to around 600 ppm, or approximately 0.06%, by the end of the period. This decline is explained by the chemical weathering of rocks, the burial of organic matter, and the action of tropical forests, which always absorb CO2, even as they gradually shrink. This decrease reduces the greenhouse effect and accentuates cooling, facilitating the expansion of the Antarctic ice sheets. The expansion of Antarctic ice transforms ocean circulation. Cold, dense waters plunge to the depths, forming powerful currents around the continent. This flow thermally isolates Antarctica and promotes ice expansion. In parallel, sea levels drop, as a significant portion of water is trapped as ice. In coastal areas, the advance of continental shelves creates new marine habitats. Sediments preserve the memory of these upheavals, revealing the close connections between ice, oceans, and atmosphere. On the continents, cooling alters vegetation. In tropical areas, dense forests recede, gradually replaced by grasslands. Two major types of plants emerge: C3, adapted to cool or moderate climates, and C4, more efficient in heat and strong light. The latter make better use of carbon dioxide, especially when it becomes scarcer. This transition shapes new, more open landscapes, as evidenced by fossilized pollen and plant remains found in sediments. The expansion of grasslands also transforms the fauna. Many herbivores adapt to these open environments, developing more robust teeth to chew tough, silica-rich grasses. Ungulates with high molars or thick enamel become more common in fossils. Meanwhile, arboreal animals lose their habitat, while species adapted to plains thrive. The drop in sea levels alters migration routes, opening new paths between continents. This evolution gradually shapes new animal communities. In marine sediments, the clearest signal of this cooling remains the rise in delta-18 oxygen, indicating the increasing storage of fresh water in ice. As Antarctic ice sheets grow, they increase solar reflection, cool the atmosphere, and stabilize the climate. The decrease in carbon dioxide reinforces this process while altering terrestrial ecosystems. It's a self-sustaining cycle. More ice leads to more cooling. Gradually, Antarctica becomes a permanently frozen pole. With cooling, seasons become more pronounced in subtropical regions. Rainfall becomes scarcer in some places, favoring C4 grasslands, well adapted to heat and light. C3 plants, more sensitive to the lack of water, remain confined to humid areas. This transition creates mixed landscapes, where forests fragment in favor of grasses. These new habitats alter animal living conditions, gradually leading to a reorganization of fauna. The Oligocene cooling leads to more structured ocean circulation, with denser polar waters feeding deep ocean rotation. The Antarctic glaciation creates a circumpolar corridor that further isolates the continent, accentuating the thermal contrast between low and high latitudes. Isotopic records confirm this separation, with a distinct delta-18 oxygen signature between polar and temperate waters. This stabilizes the Antarctic ice sheet and marks the beginning of a new geological chapter. During the Rupelian and Chattian, the continents progressively drew closer together, altering marine currents, the salinity, and the temperature of the oceans. These changes stimulated the diversification of both baleen and toothed whales and the emergence of new groups of fish, such as gadiforms. The oceans also hosted powerful lamniform sharks, capable of maintaining an internal temperature higher than the surrounding water. This period marked major advances in the evolution of marine fauna. Baleen whales from the Oligocene show great diversity in their sizes, shapes, and lifestyles. They use baleen plates to filter small prey like plankton while expelling water. Some specialize in surface feeding, while others explore deeper waters. Fossils reveal modifications in the inner ear, a sign of enhanced echolocation. Climatic changes, particularly cooling and changes in ocean currents, encouraged this diversification. These adaptations marked a turning point in the evolution of baleen whales. Toothed whales, also known as odontocetes, also emerged during the Oligocene, developing advanced echolocation capabilities. Unlike baleen whales, they have teeth and can actively hunt various prey, such as fish and cephalopods. During this period, odontocetes diversified and inhabited several marine environments, from the continental shelf to deeper waters. The evolution of their nasal structures and echoreception marked major advancements, enhancing their ability to capture prey in varied ecological niches. The Charleston deposit, located on the southeast coast of the United States, is one of the notable discoveries from the Oligocene. It contains fossils of 25 basal cetacean species, closely related to the ancestors of modern whales. These fossils reveal significant anatomical diversity, notably in the caudal vertebrae, suggesting that the whip-like fin, characteristic of modern whales, was beginning to develop. Some Charleston species shared coastal zones and food resources, illustrating the rapid evolutionary dynamics of cetaceans at the time and the variety of ecological niches present in the Oligocene oceans. Gadiform fish, such as cods, whiting, and haddock, played a major role in the marine world of the Oligocene. Although their ancient forms differ from those we know today, these fish are characterized by long fins, a fusiform body, and specialized dentition for capturing various prey. Their geographical range extended from shallow coastal basins to open waters, where they adapted to varying conditions of salinity and temperature. This ecological flexibility enabled them to thrive and begin their diversification, thereby consolidating their role in the Oligocene marine ecosystem. Lamniform sharks, characterized by a hydrodynamic silhouette, conical snout, and a large mouth with sharp teeth, represented an impressive group of predators in the marine fauna of the Oligocene. These sharks, sometimes over 3 meters, 10 feet in length, developed a unique ability to maintain a body temperature higher than the surrounding waters, offering them a more efficient metabolism for hunting. Thanks to this gigantothermy mechanism, they could thrive in cooler waters, hunting in varied environments. Their ecological diversity within the Oligocene, from coastal areas to deeper regions, demonstrates their great adaptability. Within the marine ecosystems of the Oligocene, species diversity manifests through a complex food chain where plant and animal plankton play a fundamental role. Small fish and crustaceans feed on this plankton, subsequently serving as prey for larger species such as gadiforms and some odontocetes. Baleen whales filter water to build up fat reserves, while lamniform sharks dominate hunting areas, pursuing both fish and younger cetaceans. Each group finds its specific niche, allowing for varied ecological interactions and ongoing evolution of the lineages that would shape marine biodiversity in subsequent eras. The fauna evolves towards more familiar forms, with species that, in some cases, reach gigantic sizes, and others that embark on bold migrations. This chapter focuses on terrestrial life during this period, highlighting large land mammals, the evolution of primates, marine birds, and the persistence of formidable predators from South America. Recent discoveries offer us a fascinating glimpse into the diversity of creatures inhabiting the plains, forests, and coastal areas of the Oligocene. One of the most impressive creatures of the Oligocene is Paraceratherium, a hornless rhinoceros that was one of the largest land mammals ever known. Measuring more than 5 meters or 16 feet at the shoulder and weighing up to about 10 tons or 20,000 lbs, it dominated the landscape of its time. Although the fossils are partial, they reveal that it surpassed in size most of the other large contemporary mammals. This giant belonged to the perissodactyls, a family that includes today's horses, rhinoceroses, and tapirs. Herbivorous, Paraceratherium probably fed on foliage it could reach thanks to its great height, accessing levels inaccessible to other animals. In 2021, a team of researchers identified a new species of Paraceratherium, Paraceratherium lynxiaense, dating back 26.5 million years. The fossils, discovered in Asia, revealed new information on the geographical distribution of this gigantic mammal. 3 years later, a thorough analysis of the fossils was conducted using X-ray microtomography, a technique that allows obtaining detailed 3D images. This method enabled scientists to observe the structure of blood vessels in the neck region, a crucial aspect for understanding how this immense animal managed blood circulation in its long neck. The researchers suggested that this unique vascularization allowed for maintaining adequate blood pressure, especially when Paraceratherium raised its head to graze on vegetation at heights. During the Oligocene, the evolution of catarrhine primates took an important turn. These primates, which include Old World monkeys and great apes, mainly developed in Africa. The continent offered ideal tropical and subtropical forests for their growth, despite a certain geographic isolation. The fossils found, notably of propliopithecids, show a slow diversification of these primates, with varied dental adaptations allowing them to grind fruits, leaves, and sometimes insects. This group set the stage for lineages that later would give rise to forms closer to humans. The Oligocene is also a period where rodents, such as hystricomorphs, which include modern species like guinea pigs, porcupines, and chinchillas, experienced surprising dispersal. These small mammals might have crossed the Atlantic by clinging to natural vegetation rafts, drifting with ocean currents. Although it may seem improbable, similar events have been observed in modern history, where animals have traveled on masses of plant debris. On geological timescales, these rare events allowed these rodents to colonize new ecosystems, explaining their presence on different continents. The Oligocene marks an important step in the evolution of avifauna, with the emergence of groups of modern birds, such as frigates and albatrosses. Frigates, nicknamed pirate birds, due to their habit of stealing food from other seabirds, are remarkable gliders, capable of remaining in flight for long periods. Albatrosses, meanwhile, are famous for their long-distance flights, covering thousands of kilometers or miles using winds and currents. Their presence at this time shows that they had already begun to occupy the vast marine expanses, despite a cooler late Oligocene climate. However, their exact distribution remains debated, as well-preserved fossils are rare. A fascinating discovery from the Oligocene concerns the existence of cebichids, late terrestrial crocodilians. Contrary to the classic image of a crocodile living in water, the cebichids were adapted to terrestrial life. Their morphology, with longer and straighter legs, as well as their dentition, suggests they actively hunted on the ground, possibly scavenging. Traditionally associated with South America, these crocodilians have been found in fossils dated from the late Cretaceous and Paleogene. However, in 2025, a fossil discovered in the Caribbean shows that they may have survived until the late Oligocene, persisting on islands or in isolated coastal areas. This discovery suggests a closer link between the faunas of South America and the Caribbean, with potentially maintained cebitid populations on island refuges. The cebitids, which survived during the Rupelian and Chattian of the Oligocene, show a remarkable ability to adapt to the conditions of the end of this period. Although the climatic fluctuations of the Oligocene were not as extreme as during other geological periods, they certainly influenced the availability of terrestrial habitats and prey. In a world where herbivorous mammals were diversifying, opportunistic predators like the cebitids could easily find food. Island and coastal ecosystems played a key role in allowing the conservation of some older species, as geographical isolation limited competition with new animal forms. The existence of these late terrestrial crocodilians bears witness to the ecological diversity of the era, a world populated by giant herbivores, evolving primates, pioneering rodents, and birds adapted to wide spaces. Yet, this world was also in full transformation. Every Oligocene fossil enriches the portrait of an Earth in transition. Paraceratherium embodies the grandeur of hornless ungulates, while the first catarrhine primates foreshadow the lineage of Old World monkeys. Hystricomorph rodents began an expansion that would permanently mark animal history. Already, birds like frigates or albatrosses show adaptations similar to those of today. And in the Caribbean, the late presence of cebitids reminds us that some ancient lineages managed to survive for a long time before disappearing or transforming. The faunal diversity of the Oligocene continues to fascinate researchers. Thanks to advanced tools like micro-CT scanning or chemical analysis of bones, it is now possible to trace an animal's growth, its diseases, or its diet. Every detail counts, whether it's understanding how a giant like Paraceratherium managed its blood circulation or how small rodents crossed the ocean. Recent discoveries show how paleontology constantly evolves, sometimes questioning what was thought to be established. Each fossil enriches the narrative of a world in transition, where past and future intertwine. At the end of the Oligocene, the Earth experiences profound climatic and geological upheavals. This period, marked by the Rupelian and Chattian, sees the emergence of a key phenomenon, the OCIM, or Oligocene carbon isotope maximum. Around 25 million years ago, an increase in carbon-13 is observed in the geological records, indicating a significant reshuffling of carbon reserves between the ocean and the atmosphere. This change, although subtle on paper, has major consequences on marine and terrestrial ecosystems. To understand the positive excursion of delta-13 carbon, it's essential to know that carbon isotopes circulate among three major reservoirs: the atmosphere, the ocean, and the biosphere. Delta-13 measures the proportion of carbon-13 relative to carbon-12. When this value increases, it means that marine records like foraminiferal skeletons or calcareous sediments contain more carbon-13 than usual. This signal reflects a significant change in the way carbon is stored or recycled in the environment. Towards the end of the Oligocene, the climate depended on a delicate balance between carbon dioxide, the forming Antarctic ice, and the movements of tectonic plates. The OCIM phenomenon seems to reflect a disturbance in the carbon cycle between the ocean and the atmosphere. Some researchers believe that marine life captured more carbon thanks to more active photosynthesis. This could be linked to an increase in upwelling, stimulating plankton growth and carbon storage. Upwelling refers to the rising of deep, nutrient-rich waters, such as nitrates or phosphates. It occurs when surface winds push water offshore, or in certain oceanic divergence zones. These nutrients stimulate phytoplankton, microscopic algae that capture carbon dioxide through photosynthesis. When they die, some of this carbon is transported to the bottom and trapped in sediments for millennia. More intense upwelling can thus lead to increased carbon sequestration, visible in geological records. During the Rupelian, and especially the Chattian, tectonics altered oceanic circulation. The expansion of mid-ocean ridges, like the East Pacific Rise, changed the shape of ocean basins and influenced deep currents. When a ridge is very active, it takes up more space, reducing the available space for water and causing sea levels to rise. Conversely, if its activity slows, the sea can fall. This global phenomenon is called eustasy, and its evolution partly depends on the volume taken by these expanding or retreating ridges. Sea level variations are reflected in sedimentary basins by alternations of shallow marine and deeper sediment layers. During the OCIM, these changes transformed coastal environments, estuaries, and littoral plains, affecting local fauna and flora. A sea level rise could submerge forests and grasslands, while a retreat would create new habitats for plants adapted to emerging soils, thus influencing the distribution of resources and species. At the end of the Oligocene, marine life evolved with the climate. Bony fish had to adapt to cooler surface waters, a consequence of the expansion of Antarctic ice. The development of upwellings enhanced ocean productivity, attracting zooplankton, crustaceans, and fish in large numbers. This abundance fed powerful predators, such as the first marine mammals, or large predatory fish. In this changing ocean, the food chain was reorganized. During the OCIM, baleen and toothed whales, although older, adapted to changes in ocean circulation and food resources. Temperate waters rich in nutrients, as well as thermal fronts, provided ideal habitats for hunting and reproduction. The upwelling, by stimulating plankton and fish growth, created food-rich zones, favoring the diversification of marine mammals. At the end of the Oligocene, progressive climatic changes altered dominant vegetation types, such as subtropical and tropical forests, influenced by sea level fluctuations and temperatures. Pollen fossils show that humid environments evolved into dry plains as the sea retreated. Meanwhile, mangrove or swamp deposits formed in areas where the sea advanced onto the land. The transformations of the Oligocene result from a complex balance between tectonics, climate, and ocean chemistry. Tectonics reshaped the continents, mid-ocean ridges altered seafloors, and the reduction in carbon dioxide led to global cooling. During the OCIM, the increase in carbon-13 indicates a disruption of the carbon cycle, likely linked to intensified upwelling. Faced with these changes, fauna and flora adapted. Whenever a current forms or an area is enriched with nutrients, life establishes itself, organizes, and transforms. One hypothesis proposed to explain the rise in carbon-13 is that more organic matter was trapped in marine sediments. Other researchers suggest, conversely, a decrease in light carbon due to less erosion of the continents or a change in vegetation. As often, several factors combine. Through ocean drilling, scientists analyze sediments, carbonate chemistry, and planktonic fossils to reconstruct the dynamics of carbon in the oceans. The OCIM shows how ecosystems react to long-term variations in the carbon cycle. At the end of the Oligocene, thermohaline circulation begins to form, creating contrasts in marine productivity. The upwelling phenomenon, which brings up nutrients, plays a key role in the diversification of marine species and the enrichment of the food chain. These complex interactions between life and the planet help us better understand the impact of climate change on ecosystems. Surface productivity variations influence the feeding behavior of many species. Some seabirds focus on fish shoals near upwelling zones, while mammals prefer to hunt further away, where competition is lower. During periods of high productivity, some microscopic algae experience spectacular booms. This changes the composition of marine communities and leaves visible traces in the sediments, such as an accumulation of diatoms or calcareous algae. Ridges are areas where oceanic crust forms. When they become very active, they raise the ocean floor, reducing the space available for water. The result, sea levels rise over the continents. During a transgression, the sea advances and covers the lands, sometimes even burying fossil forests. During a regression, it retreats, revealing ancient eroded soils or temporarily exposing them to the open air. The progressive isolation of Antarctica, the formation of a new oceanic circulation, and the emergence of maritime pathways modify global dynamics. This readjustment of the carbon cycle between the ocean, atmosphere, and biosphere heralds slow but decisive transformations. The glaciation that will follow and the reorganization of ocean currents will shape ecosystems, laying the groundwork for the changes of the Miocene. The Oligocene carbon isotope maximum reveals how carbon can be rapidly redistributed between the ocean, the atmosphere, and the biosphere. Even in a period considered stable, transient upheavals can alter marine chemistry and surface currents. The intensification of upwelling, the reorganization of plankton, and variations in sea level bear witness to this. These changes depict a world in constant adaptation, where life seizes every new opportunity. The fluctuations observed in sedimentary records reveal that the OCIM occurs within a context of progressive cooling and the evolution of nascent ice sheets. Although this episode does not last millions of years, it leaves a distinct geochemical signal, illustrating a key moment in optimizing carbon sequestration. Studying this event is essential to understanding climatic mechanisms and the continuous transformations of the planet, shaped by its internal movements and interactions with the biosphere. At the end of the Oligocene, the world changes profoundly. The increase in carbon-13 signals an upheaval in carbon storage. The seas advance, then retreat, forcing life to constantly adapt. Upwelling feeds marine chains, and variations in sea level redraw the shores. Sediments hold the memory of these transformations, where climate, tectonics, and biodiversity intertwine. What the OCIM reveals is that no balance is fixed. The Earth reacts to every tiny variation, always ready to change, even in its calmest phases.